The universe is full of stars, each one different in size, brightness, and lifespan. Among them are giants so enormous that they make our own sun look small by comparison. Astronomers have studied countless stars across the cosmos, but one stands out as the largest ever discovered. Its size is almost beyond comprehension, stretching so wide that if it replaced the Sun at the centre of our solar system, its surface would extend far past the orbit of Jupiter. Why is it so extreme, and what does it tell us about the universe? Before we dive in, tell us in the comments below where in the world you're watching from and what time it is there now. So, settle in for a journey to the biggest stars ever found in the universe. The Sun is the great star that lies at the very centre of our solar system. It is an enormous, almost perfectly round ball made of extremely hot plasma. Deep inside its core, powerful nuclear fusion reactions take place, and these reactions generate an enormous amount of heat and energy. The Sun glows brightly because of this process, and it sends its energy out into space as light and heat. Most of this energy reaches us as visible light and infrared radiation, while about 1/10 of it comes in the form of ultraviolet rays. For Earth, the Sun is without question the most important source of energy, as all life depends on the warmth and light it provides. Since ancient times, the Sun has been worshipped in many cultures, often seen as a sacred force, while also being one of the earliest and most central subjects of astronomical study. The Sun does not stay still in the universe. Like all stars in the Milky Way, it orbits around the galactic centre. Its path lies at a distance of roughly 24,000 to 28,000 light-years from that centre. The Sun's distance from Earth is so important that astronomers use it as a standard unit of measurement. This distance is called the astronomical unit, and it equals about 149,600,000 kilometres. In terms of light travel, the Sun is about 8 minutes away from us, meaning that the sunlight we see now actually left the Sun 8 minutes earlier. The Sun itself is huge. Its diameter measures about 1,391,400 kilometres, which is about 864,600 miles. To put this into perspective, the Sun is about 109 times wider than Earth. It is also far more massive. Its mass is about 330,000 times greater than Earth's, and it makes up about 99.86% of all the mass in the entire solar system. The outer layer of the Sun, known as the photosphere, is mostly made of hydrogen, which makes up about 73% of it, and helium, which makes up about 25%. There are also tiny amounts of heavier elements, including oxygen, carbon, neon, and iron. Astronomers classify the Sun as a G-type main sequence star, or G2V star for short. Informally, it is sometimes called a yellow dwarf, although in truth the light it gives off is white, not yellow. The Sun was born about 4,600,000,000 years ago. It formed when part of a giant cloud of gas and dust collapsed under the pull of gravity. Most of the material was drawn into the centre to form the Sun, while the rest spread out into a flat disk. Over time, this disk gave rise to the planets, moons, asteroids, and comets of the solar system. At the centre, conditions became so hot and dense that nuclear fusion began, and the Sun started to shine. Inside the core of the Sun, this process continues even today. Every single second, about 600 billion kilograms of hydrogen are fused into helium. In this process, about 4 billion kilograms of matter are transformed directly into energy. This is the energy that floods the solar system and makes life on Earth possible. But the Sun, like all stars, will not shine forever. In about 4 to 7 billion years, it will run out of hydrogen fuel in its core. When that happens, the balance that holds it together, known as hydrostatic equilibrium, will no longer exist. Its core will become much denser and hotter, while its outer layers will swell outward. At this stage, the Sun will transform into a red giant, growing so large that it might even engulf some of the inner planets. After this phase, scientists believe the Sun will shed its outer layers into space, leaving behind only its hot core. This core will shrink into what is called a white dwarf, a very dense and slowly cooling remnant star. Although it will no longer produce new energy through fusion, it will continue to glow faintly, giving off the last of its stored heat for perhaps trillions of years. In the farthest future, after this cooling process ends, it is thought the Sun will become a cold, dark object called a black dwarf, with almost no energy left to release. The word sun in English has a long history. It comes from the Old English word sunne. Related words can be found in other Germanic languages, such as West Frisian sinne, Dutch zon, Low German sun, Standard German sonne, Bavarian sunna, Old Norse sunna, and Gothic sunno. All of these terms go back to the Proto-Germanic word sunnun. This, in turn, is linked to words for the sun in other branches of the Indo-European language family. In many of those languages, the root of the word uses an L instead of an N. For example, in Latin the word for sun is sol. In ancient Greek it is helios. In Welsh it is hall. In Czech it is slunts. In Sanskrit it is svar. And in Persian it is exvar. Interestingly, the L form also survived in Proto-Germanic, where it appeared as solen. This form gave rise to words like Gothic sal and Old Norse sol. Through this line, we get the modern Scandinavian words for sun, such as Swedish and Danish sol and Icelandic sol. In English today, the most common descriptive word related to the sun is sunny. In more technical or scientific contexts, however, the term solar is used, which comes from the Latin word sol. From Greek we also get the rare adjective heliac, which comes from helios. In literature and poetry, both the Latin and Greek names appear as personifications of the sun, Sol and Helios. In science fiction, the name Sol is sometimes used to make it clear that we are speaking about our sun rather than some other star. Astronomers also use the word Sol in another sense. It refers to the length of a day on another planet, such as Mars, measured according to that planet's rotation in relation to the sun. The sun is what astronomers call a G-type main sequence star, which means it belongs to the category of yellow medium-sized stars that are steadily burning hydrogen in their cores. Despite being only one star out of the countless stars in the universe, the sun completely dominates our solar system. In fact, it makes up about 99.86% of the total mass of everything within the solar system. This means that almost all the weight of the solar system comes from the sun, while the planets, moons, asteroids and comets together contribute only a tiny fraction. The brightness of the sun is also impressive when compared with other stars. Astronomers measure the absolute brightness of stars using something called absolute magnitude, and the sun's value is plus 4.83. This places it among the brighter stars of our galaxy. It is estimated that the sun shines more brightly than about 85% of the stars in the Milky Way galaxy, which contains hundreds of billions of stars. Most of the stars in our galaxy are faint red dwarfs, which are much smaller and dimmer than the sun. In terms of size and mass, the sun also surpasses the majority of stars around it. It is more massive than about 95% of all stars within a distance of 7 parsecs, which is about 23 light-years. The sun belongs to a category of stars called population 1 stars, which are rich in heavier elements. These heavy elements, as astronomers describe them, are anything heavier than hydrogen and helium, the two most basic elements that filled the universe after the Big Bang. The sun formed about 4.6 billion years ago, and scientists think that its birth may have been triggered by the shockwaves from one or more nearby exploding stars called supernovae. Evidence for this idea comes from the fact that the solar system contains unusually high amounts of heavy elements such as gold and uranium compared to older metal-poor stars known as population 2 stars. These heavy elements could only have been produced in extremely powerful processes, either inside massive stars where atomic nuclei absorb neutrons, or during the cataclysmic explosions of supernovae. In our sky, the sun is by far the brightest object. It has an apparent magnitude of -26.74, which makes it about 13 billion times brighter than the next brightest star in our sky, Sirius, which has an apparent magnitude of -1.46. This is why the sun completely outshines every other star during the day. Astronomers measure distances within the solar system using a unit called the astronomical unit. One astronomical unit is defined as the average distance between the Earth and the Sun, which is about 150 million kilometers, or about 93 million miles. However, this distance is not constant. Because Earth follows an elliptical orbit, the distance changes by about plus or minus 2.5 million kilometers, or about 1.6 million miles. The closest point of Earth to the Sun, called perihelion, happens around the 3rd of January, while the farthest point, called aphelion, occurs around the 4th of July each year. At the average distance between Earth and the Sun, light from the Sun takes about 8 minutes and 20 seconds to reach us. When Earth is at its closest, the sunlight arrives about 2 seconds faster. This steady flow of light is not just what makes daytime possible, it is the fundamental source of nearly all life on our planet. Plants use sunlight to carry out photosynthesis, which forms the foundation of the food chain. Sunlight also drives Earth's climate and weather systems, shaping everything from winds to rainfall. The sun does not have a solid surface or a sharp edge. Instead, its outer layers gradually become less dense as you move upward. For practical purposes, scientists define the sun's radius as the distance from its center to the visible layer we call the photosphere, which is the part of the sun that we actually see glowing in the sky. The sun is almost a perfect sphere, but not exactly. The difference between its radius at the equator, where it bulges slightly due to rotation, and its radius at the poles is called ablateness. Measuring this tiny difference is extremely difficult. Observations must be done from satellites above Earth's atmosphere, since atmospheric distortion makes ground-based measurements unreliable. For a long time, astronomers wondered if the sun's ablateness could explain the strange motion of Mercury's orbit, known as the perihelion precession. However, Albert Einstein showed that his theory of general relativity could fully explain Mercury's orbit even if the sun were a perfect sphere. Later, highly precise measurements by instruments aboard the Solar Dynamics Observatory and the Picard satellite confirmed that the sun's ablateness is incredibly small, only about 8 parts per million, or 8.2 times 10 to the power of -6. This makes the sun the most perfectly spherical natural object ever measured in the universe. Interestingly, this tiny degree of ablateness does not change even when the sun's level of radiation varies, and the gravitational pull from the planets does not significantly alter the sun's shape either. The sun also rotates, but not like a solid ball. It spins faster at its equator than it does at its poles, a phenomenon called differential rotation. This is caused by the churning motion of hot gases inside the sun combined with the influence of the Coriolis force, which is related to rotation. If we use the distant stars as a frame of reference, the sun takes about 25.6 days to complete one rotation at its equator, but about 33.5 days at its poles. From Earth, as our planet moves around the sun seems to rotate once roughly every 28 days. Seen from above the sun's north pole, the sun rotates counterclockwise around its axis. When the sun was young, it spun much faster than it does today. Studies of stars similar to the sun suggest that billions of years ago, the sun may have rotated up to 10 times faster. Back then, its surface would have been far more turbulent, with intense storms, stronger X-ray and ultraviolet radiation, and vast numbers of sunspots, possibly covering between 5% and 30% of its surface. Over time, the sun slowed down because its powerful magnetic field interacted with the stream of charged particles flowing outward, known as the solar wind. This process, called magnetic braking, gradually reduced its rotation speed. Even so, the sun still carries a memory of its ancient rapid spin deep in its interior. The core of the sun rotates at a much faster rate than the surface, about once every 7 days, which is roughly 4 times faster than the average speed at the surface. The sun is made mostly of just 2 elements, hydrogen and helium. In its current stage of life, hydrogen makes up about 74.9% of the mass of the sun's outer layer, which astronomers call the photosphere. Helium follows as the second most common element, accounting for about 23.8%. All the other elements combined, which astronomers group together under the word metals, form less than 2% of the sun's mass. Among these heavier elements, oxygen is the most abundant, making up roughly 1% of the sun's mass, followed by carbon at about 0.3%, neon at around 0.2%, and iron also at about 0.2%. The sun's original chemical mixture came from the vast interstellar cloud of gas and dust out of which it was born. In those earliest days, before nuclear fusion began in its core, the sun's composition would have been about 71.1% hydrogen, 27.4% helium, and 1.5% heavier elements. The hydrogen and most of the helium had been created far earlier, during the first 20 minutes after the universe came into existence, through a process called Big Bang nucleosynthesis. The heavier elements, however, were not born then. Instead, they were created much later inside earlier generations of stars. When those stars reached the end of their lives, especially in dramatic explosions known as supernovae, they released these heavy elements into space, enriching the interstellar medium and eventually giving rise to the Sun. Since the Sun's birth about 4.6 billion years ago, the central process powering it has been nuclear fusion, where hydrogen is converted into helium under immense pressure and heat. Since the Sun's birth about 4.6 billion years ago, the central process powering it has been nuclear fusion, where hydrogen is converted into helium under immense pressure and heat. This transformation has slowly but steadily changed the balance of elements inside the Sun. In the very beginning, the helium at the Sun's core made up about 24%, but over billions of years of fusion, that number has risen to about 60%. Gravity has also caused some of the helium and the heavier elements to sink toward the center of the Sun, leaving the photosphere with slightly less of these elements than it once had. Interestingly, the amount of heavier elements overall has not really changed. What has shifted is where they are located within the Sun. The heat from the Sun's core does not rise upward through bubbling convection, like boiling water on Earth, but instead travels outward mainly through radiation. That means the helium and other fusion products remain trapped in the core, gradually forming a dense inner region of helium that cannot yet undergo further fusion. This is because the Sun's core, though incredibly hot and dense, is not yet extreme enough to fuse helium. Today, the Sun's photosphere shows a reduced amount of helium, and the concentration of metals is only about 84% of what it was before nuclear fusion began. Looking ahead, as helium keeps building up in the core, the Sun will eventually exhaust its hydrogen fuel. In about 5 billion years, this change will force the Sun to leave the stable main sequence phase of its life and expand into a red giant star. Astronomers often consider the chemical composition of the Sun's photosphere as a good reflection of what the early solar system was made of. To measure the amounts of these elements, scientists use two main methods. One is spectroscopy, which studies the light from the Sun's surface to identify the fingerprints of different elements. The other is the study of certain meteorites, which have remained unchanged since the early solar system. These meteorites never melted and therefore preserve the original composition of the protostellar Sun. Remarkably, both methods of measurement give results that agree with each other. At the center of the Sun lies its core, which stretches from the very middle to about 1/5 to 1/4 of the Sun's total radius. This core is incredibly dense, with material packed up to 150 grams in every cubic centimeter. That is about 150 times denser than water. The temperature is even more staggering, reaching about 15.7 million Kelvin. By contrast, the surface of the Sun, which glows to us as sunlight, is far cooler at about 5,800 Kelvin. Recent studies using data from the SOHO spacecraft suggest that the core might actually rotate faster than the layers of the Sun just outside it. Throughout nearly all of the Sun's life so far, its energy has been generated in the core by a nuclear process known as the proton-proton chain. In this chain, hydrogen nuclei collide and merge to form helium, releasing enormous amounts of energy in the process. Currently, about 0.8% of the Sun's energy comes from a different fusion process known as the carbon-nitrogen-oxygen cycle, or CNO cycle. This contribution is expected to grow larger as the Sun gets older and brighter. The Sun's core is the only part where significant fusion takes place. About 99% of the Sun's total energy comes from the inner 24% of its radius. Beyond about 30% of the radius, almost no fusion occurs. The rest of the Sun is heated by energy that slowly moves outward from the core through countless interactions, until it finally escapes into space as light and particles. Inside the core, the proton-proton chain is happening an unimaginable number of times, around 9.2 times 10 to the power of 37 reactions every second. These reactions transform about 3.7 times 10 to the power of 38 protons into helium nuclei, or alpha particles, every second. Altogether, this amounts to about 6.2 times 10 to the power of 11 kilograms of matter being fused every second. Despite this, each individual proton takes, on average, about 9 billion years before it fuses with another through this chain. When 4 hydrogen nuclei fuse into a single helium nucleus, about 0.7% of the mass is released as pure energy. This means the Sun is constantly turning about 4.26 billion kilograms of matter into energy every second. To achieve this, it must burn through about 600 billion kilograms of hydrogen each second. The total energy released is about 384.6 yottawatts. That is 3.846 times 10 to the power of 26 watts. Put another way, This is equal to more than 9.192 times 10 to the power of 10 megatons of TNT exploding every single second. Even though the Sun's total output is so immense, the energy produced in each tiny unit of its core is actually not extreme by everyday standards. In fact, theoretical models show that the maximum energy produced at the very centre is about 276.5 watts per cubic metre, which is about the same power density as inside a pile of compost here on Earth. The difference is that the Sun's core is so enormous and so dense that, when all those cubic metres are added together, the total becomes overwhelmingly large. The Sun's fusion rate is kept steady by a natural balancing act. If fusion speeds up slightly, the core gets hotter and expands, which lowers the density and slows fusion back down. If fusion slows, the core cools and contracts, which raises the density and speeds fusion up again. This self-correcting system keeps the Sun's energy output stable, allowing it to shine reliably for billions of years. The radiative zone is the thickest and most massive layer inside the Sun. It stretches outward from the core beginning at about 0.25 of the Sun's radius and ending at around 0.7 of the Sun's radius. Altogether, it is about 0.45 of the Sun's radius in thickness. In this wide region, the main way that energy moves outward is not by large currents or motions of matter, but instead by radiation. This means that energy, produced in the core through nuclear fusion, travels in the form of light and heat slowly leaking outward from one layer to the next. At the very bottom of the radiative zone, close to the core, the temperature is close to 7 million kelvins. By the time we reach the top of this region, near 0.7 of the Sun's radius, the temperature has fallen to around 2 million kelvins. Even though this is an enormous drop, the change is still too small compared to what would be needed to create convection. Because of this, there are no rising and falling currents in the radiative zone, and the transfer of energy happens mainly by radiation, instead of by the movement of hot plasma. The way this radiation works is quite slow and inefficient. The plasma here is so dense that photons, which are tiny packets of light and energy, cannot travel far. They are constantly absorbed and re-emitted by the ions of hydrogen and helium. A single photon may only travel a very short distance before being captured and sent out again, making its journey from the core to the outer layers a process that takes hundreds of thousands of years. The density of material also changes dramatically across this zone. At about 1/4 of the Sun's radius, the density is extremely high, around 20,000 kilograms per cubic meter. But near the top, at about 0.7 of the Sun's radius, the density has dropped to only about 200 kilograms per cubic meter. This is a decrease by a factor of 100. Above the radiative zone lies a very important boundary layer called the Tacocline. This is the thin transition region between the radiative zone and the convection zone. In the radiative zone below, the Sun rotates almost like a solid body, with every part turning at nearly the same speed. In the convection zone above, however, the rotation is different, with some parts spinning faster than others. The Tacocline is where these two very different behaviours meet, creating a powerful shear, layers of gas sliding past each other at different speeds. Many scientists believe that this region is crucial for generating the Sun's magnetic field through a process called the solar dynamo. The convection zone begins at about 0.7 of the Sun's radius, which is roughly 500,000 kilometers below the surface, and it stretches all the way to the visible surface. In this zone, the plasma is not dense or hot enough to transfer energy efficiently by radiation alone. Instead, convection takes over. Here, heat is moved by large masses of plasma rising and falling, much like boiling water in a pot. At the base of the convection zone, plasma gets heated by the underlying Tacocline. As it warms, it expands, which makes it less dense. This lower density causes it to rise upward toward the surface. On its way up, it carries heat outward. When it reaches the upper layers near the surface, it begins to cool. As it cools, its density increases again, and it sinks back down toward the base of the convection zone. This cycle repeats endlessly, carrying the Sun's energy from deep inside toward the outermost layers. By the time we reach the photosphere, which is the visible surface of the Sun, the temperature has dropped dramatically. It is now only about 5,700 kelvins, which is about 9,800 degrees Fahrenheit. This is around 350 times cooler than the deep interior of the Sun. The density has also fallen to an incredibly small value of only 0.2 grams per cubic meter. This is about 1/10,000th the density of air at Earth's sea level, and about 1/1,000,000th the density found in the deeper part of the convection zone. The movements of the plasma in the convection zone create visible patterns on the Sun's surface. The surface appears to be broken into small grain-like structures known as solar granules. These are formed by the tops of the convection cells, where hot plasma rises in the bright centers and cooler plasma sinks back down along the darker edges. At larger scales, these patterns are called supergranulation. The plasma cells in this layer are shaped like three-dimensional hexagons, similar to Bénard cells seen in fluids on Earth. The turbulent movements in this region also help sustain small-scale magnetic fields near the surface. Above the convection zone lies the solar atmosphere. This is the outer part of the Sun that stretches from the photosphere upward into space and eventually blends into the heliosphere, the vast bubble of solar wind that surrounds the entire solar system. The solar atmosphere is usually divided into three main layers: the photosphere, the chromosphere, and the corona. Between the chromosphere and the corona lies a very thin but important transition region, which some researchers treat as its own distinct layer. The photosphere is what we see as the Sun's shining surface. It is the layer where the Sun becomes opaque to visible light. Photons that escape from this layer are no longer reabsorbed and instead travel freely through space, reaching Earth as sunlight. The thickness of the photosphere is only a few tens to a few hundreds of kilometers, which is extremely thin compared to the size of the Sun. The photosphere is cooler at the top than at the bottom. This temperature difference makes the center of the Sun's disk look brighter than the edges when viewed from Earth. This effect is called limb darkening. The sunlight we see has a spectrum similar to that of a black body at about 5,772 kelvins, but with extra dark lines caused by atoms in the outer layers absorbing specific wavelengths. The density of particles here is about 10 to the power of 23 per cubic meter, which is less than 1/2 of 1% of the number of particles in the same volume of Earth's atmosphere at sea level. Interestingly, the photosphere is not fully ionized. Only about 3% of the hydrogen atoms here are ionized, while the vast majority remain neutral. Above the photosphere lies the coolest layer of the Sun, known as the temperature minimum region. It extends to about 500 kilometers above the surface and has a temperature of only around 4,100 kelvins. This is cool enough for simple molecules such as carbon monoxide and water to exist, which would not survive in the hotter regions below or above. Just above the temperature minimum layer of the Sun lies another fascinating region, about 2,000 kilometers thick. This layer is filled with a wide range of emission and absorption lines in its spectrum. It is known as the chromosphere, a name that comes from the Greek word chroma, meaning color. The name is very fitting, because the chromosphere reveals itself as a glowing flash of color at the beginning and end of a total solar eclipse, standing out briefly against the darkened sky. The temperature inside the chromosphere does not stay constant. Instead, as we go higher and higher within it, the temperature gradually rises, reaching up to about 20,000 kelvins near the top. In the upper parts of this layer, helium atoms begin to lose some of their electrons, meaning they become partly ionized. Above the chromosphere lies a very thin but incredibly important zone known as the transition region. This layer is only about 200 kilometers thick, yet within it something dramatic happens. The temperature jumps suddenly from around 20,000 kelvins in the upper chromosphere to nearly 1,000,000 kelvins in the lower corona. This extreme increase in heat happens because helium becomes fully ionized in this region, which reduces how much energy the plasma can radiate away. As a result, the plasma heats up rapidly. The transition region does not exist at one fixed height. Instead, it moves and shifts constantly, wrapping around chromospheric features such as spicules, thin jets of plasma, and filaments. It is chaotic, never still, and appears like a shimmering, restless halo around the chromosphere. From the surface of Earth, this layer cannot be seen directly, but spacecraft with instruments sensitive to extreme ultraviolet light can observe it clearly from space. Beyond the transition region lies the corona, the outermost layer of the Sun's atmosphere. The part of the corona closest to the Sun's surface is called the low corona. Here, the density of particles ranges from about 10 to the power of 15 per cubic meter to 10 to the power of 16 per cubic meter. The average temperature of the corona and the solar wind is about 1 to 2 million kelvins, but in the hottest spots the temperature can soar to an incredible 8 million to 20 million kelvins. Scientists are still working to fully understand why the corona is so hot, far hotter than the Sun's surface. One of the known reasons is magnetic reconnection, a process in which the Sun's powerful magnetic field lines snap, rearrange, and release huge amounts of energy. At the very edge of the corona lies an invisible boundary called the Alphen critical surface. This is the point where the speed of the solar wind, which is moving outward, becomes faster than the phase speed of Alphen waves, which are magnetic waves moving inward. Below this surface, the flows of plasma are slower, while above it the solar wind races away at supersonic speeds. The height of this boundary is not the same everywhere. It changes depending on where you are around the Sun, and also on the level of solar activity. During solar minimum, it is found closer to the Sun, while during solar maximum it stretches farther outward. In April of the year 2021, this surface was crossed for the very first time by the Parker Solar Probe, which flew at distances between 16 and 20 solar radii from the Sun. Predictions suggest that the Alphen critical surface can exist anywhere between 8 and 30 solar radii depending on conditions. Farther out in space, beyond the corona, lies the vast region called the Heliosphere. The Heliosphere is defined as the area where the solar wind, streaming outward from the Sun, dominates over the surrounding interstellar medium. Inside this bubble, turbulence and other forces cannot affect the shape of the corona itself, because information cannot travel faster than the speed of Alphen waves. The solar wind continues to blow outward through the Heliosphere without stopping, carrying the Sun's magnetic field with it. As the Sun rotates, this magnetic field is twisted into a spiral pattern. The solar wind flows outward till it eventually reaches the boundary called the heliopause, more than 50 astronomical units away from the Sun. In December of the year 2004, the Voyager 1 spacecraft crossed a shock front that was believed to be part of the heliopause. Later, in the year 2012, Voyager 1 detected a sudden rise in cosmic ray impacts along with a sharp decrease in lower energy particles from the solar wind. This dramatic change showed that the probe had finally passed through the heliopause and entered the interstellar medium. The historic crossing took place on the 25th of August in the year 2012, at a distance of about 122 astronomical units, or roughly 18 terameters, from the Sun. The heliosphere also has a long trailing extension known as the heliotail, which stretches far behind the Sun as it moves through the galaxy. This tail is shaped by the Sun's peculiar motion as it drifts among the stars, marking the Sun's passage through space. The Sun shines across the entire range of visible light, meaning it gives off every colour of the rainbow. From space, or when the Sun is high in the sky, and not heavily filtered by Earth's atmosphere, its overall colour is actually white. Scientists describe this whiteness with a technical colour index of about 0.3 by 0.3 on the CIE colour scale. If you look at the Sun's light distribution from space, its brightness reaches a maximum in the green portion of the spectrum. This does not mean the Sun looks green to our eyes, but rather that green light is the strongest part of its radiation balance. When the Sun is very low in the sky, close to sunrise or sunset, its light has to travel through much more of Earth's atmosphere. Along the way, the atmosphere scatters different wavelengths of light. This scattering makes the Sun appear in a range of warm colours such as yellow, orange, red, and sometimes magenta. On rare occasions, unusual atmospheric conditions can even make the Sun appear green or blue. Across different cultures, people have imagined or described the Sun in different colours. Some see it as golden yellow, while others picture it as fiery red. The exact reasons behind these cultural associations are still debated among historians and anthropologists. Astronomers classify the Sun as a G2 star. This means it belongs to the G-type group of stars, which are medium in temperature and colour, and the 2 indicates that its surface temperature falls into the second range within that category. There is also something called the solar constant. This is a measurement of how much energy the Sun delivers to an area of space that is directly exposed to its rays. At the distance of 1 astronomical unit, that is the average distance between Earth and the Sun, the solar constant is about 1,368 watts per square metre. However, when sunlight actually reaches Earth's surface, its strength is reduced because our atmosphere absorbs and scatters some of it. On a clear day, when the Sun is directly overhead, the amount of energy at the surface is closer to 1,000 watts per square metre. If we break down the energy of sunlight at the top of Earth's atmosphere, about 1/2 is infrared light, around 2/5 is visible light, and roughly 1/10 is ultraviolet light. Fortunately for life, Earth's atmosphere blocks more than 70% of the Sun's ultraviolet radiation, especially the most dangerous shorter wavelengths. Still, the ultraviolet portion that does reach the surface has a powerful influence. It ionizes the upper layers of Earth's atmosphere on the daytime side, creating the ionosphere, a region filled with charged particles that allows radio waves to travel long distances. Ultraviolet light has other effects too. It has antiseptic properties, which means it can kill germs and be used to sterilize tools or even disinfect water. For humans, it causes both good and harmful results. On one hand, ultraviolet rays trigger the skin to produce vitamin D, which is vital for strong bones and overall health. They also cause tanning. On the other hand, too much exposure leads to sunburn and is the main cause of skin cancer. Because Earth's ozone layer filters out most ultraviolet rays, the amount that reaches the surface varies with latitude. This difference has played a major role in shaping biological adaptations, including the wide variety of human skin tones across the world. Deep inside the Sun, at its core, the story of energy transport is much slower and more complex. In the center, nuclear fusion creates extremely high-energy photons, including gamma rays. But these gamma rays do not travel far at all, just a few millimeters, before being absorbed by particles in the Sun's plasma. Each time a photon is absorbed, it is re-emitted again, usually in a slightly different direction and with a little less energy. Because of this endless cycle of absorption and re-emission, it takes an extraordinarily long time for light created in the Sun's core to actually reach its surface. Scientists estimate that this journey of a single photon can take anywhere from 10,000 years to 170,000 years. By contrast, neutrinos, tiny ghost-like particles also produced in fusion, escape almost instantly because they rarely interact with matter. Neutrinos take only about 2 1/3 seconds to travel from the Sun's core to its surface. These neutrinos carry about 2% of the Sun's total energy output. If the rate of nuclear reactions in the Sun's core were to suddenly change, it would take the Sun roughly 30 million years to fully adjust and return to balance because of the slow pace of energy transport inside. For a long time, scientists faced a puzzle known as the solar neutrino problem. Detectors on Earth consistently measured only about 1/3 of the number of neutrinos that theory predicted should come from the Sun. This discrepancy puzzled researchers for decades until the year 2001, when the phenomenon of neutrino oscillation was confirmed. This discovery revealed that neutrinos can change from one type, or flavor, into another during their journey. The Sun was indeed producing the expected number of neutrinos, but detectors were only sensitive to one type, electron neutrinos, while the other 2/3 had transformed into muon and tau neutrinos by the time they reached Earth. The Sun also has a magnetic field that is far from uniform. At its poles, the magnetic field is fairly weak, only about 1 to 2 Gauss, which is about 1/10,000th to 2/10,000ths of a Tesla. In contrast, in sunspots, dark, cooler areas on the Sun's surface, the magnetic field can reach an incredible 3,000 Gauss, which equals about 0.3 Tesla. Solar prominences, which are giant loops of plasma extending from the surface, typically have fields between 10 and 100 Gauss. The Sun's magnetic field is constantly changing in strength and shape. The most obvious variation is the famous 11-year solar cycle, during which the number and size of sunspots rise and fall in a repeating pattern. The Sun's magnetic field does not stop at its surface. It is carried outward into space by the solar wind, a continuous stream of charged particles. This flow drags the magnetic field with it, creating what scientists call the interplanetary magnetic field. In the framework of magnetohydrodynamics, the physics of electrically conducting fluids, plasma moves along magnetic field lines. Because of this, the solar wind stretches the Sun's magnetic field into long, radial lines pointing outward. If the Sun's magnetic field were a simple dipole, with opposite polarities at each pole, then the solar wind would also carry a thin current sheet along its equator. At greater distances, the Sun's rotation twists this magnetic field and current sheet into a spiral shape, called the Parker spiral, named after the astrophysicist Eugene Parker who described it. Sunspots appear as dark patches on the visible surface of the Sun, which is called the photosphere. These spots are not shadows, but areas where powerful magnetic fields rise up from inside the Sun. These magnetic fields block the normal flow of heat that usually moves upward from the sun's deeper layers. Because the heat flow is reduced in these regions, sunspots are a little cooler than the surrounding surface, and so they look darker by comparison. During a period called the solar minimum, which is the quiet part of the sun's natural activity cycle, only a small number of sunspots can be seen, and sometimes none appear at all. The ones that do form at this stage usually appear near the sun's higher latitudes, that is, closer to the solar poles. As the cycle moves toward the solar maximum, which is the most active phase, sunspots begin to appear closer to the sun's equator. This gradual shift of sunspot positions follows a rule known as Spura's law. Some sunspots can grow to enormous sizes, stretching tens of thousands of kilometers across, large enough to swallow the Earth several times over. The Sun follows a repeating pattern called the solar cycle, which lasts for about 11 years. This cycle is actually part of a larger process that spans about 22 years, called the Babcock-Leighton dynamo cycle. This longer cycle describes how the Sun's magnetic field changes, swinging back and forth between two different forms: the toroidal field, which loops around the Sun like giant rings, and the poloidal field, which resembles bar magnet lines stretching outward from pole to pole. At the height of the solar cycle, when sunspots are most common, the poloidal field at the Sun's surface is at its weakest point, while the hidden toroidal field deep inside the Sun is at its strongest. This strong internal field is created by differential rotation, meaning that different parts of the Sun rotate at different speeds, especially in the layer called the Tacocline. At this stage, magnetic forces rise upward, breaking through the photosphere and forming pairs of sunspots. These pairs are usually aligned east-west and carry opposite magnetic polarities, like the north and south poles of a magnet. Interestingly, the magnetic orientation of these pairs reverses every 11 years, a rule described by Hale's law. As the solar cycle begins to decline, energy shifts away from the toroidal field back to the poloidal field. The number and size of sunspots gradually shrink until, at the minimum of the cycle, sunspots are rare, the toroidal field is weak, and the poloidal field is strong again. Then, as a new 11-year cycle begins, the magnetic energy flips once more, and the process repeats endlessly, though always with alternating polarities. The magnetic activity of the Sun produces a variety of effects that scientists group together under the term solar activity. Powerful eruptions known as solar flares, and massive bursts of charged particles called coronal mass ejections often erupt from sunspot regions. Streams of fast-moving solar wind also flow outward from darker regions on the Sun called coronal holes. Both the ejections and the solar wind carry hot plasma and the Sun's magnetic field outward into space, filling the solar system. These events can strongly affect Earth. They cause the colourful auroras near the poles, but they can also disrupt radio signals, damage satellites, and even overload electrical grids. Over longer timescales, solar activity is believed to have influenced the very formation and evolution of the solar system. The number of sunspots is closely linked with the amount of energy the Sun sends out, known as solar irradiance. When there are many sunspots, the overall solar activity is high. When there are few, the Sun is quieter. A famous example occurred in the 17th century, when for several decades almost no sunspots were recorded. This period, called the Maunder Minimum, matched the time of the Little Ice Age in Europe, when winters were bitterly cold and summers were unusually cool. Evidence from tree rings and other natural records shows that earlier extended minima also coincided with cooler global temperatures. The photosphere of the Sun, the layer we see with our eyes, has a temperature of about 6,000 kelvins. However, the outer atmosphere of the Sun, called the corona, is far hotter, between 1 million and 2 million kelvins. This is puzzling, because normally heat should flow from hotter areas to cooler ones, yet here the corona is far hotter than the photosphere beneath it. Scientists believe that extra energy is somehow being transported upward to heat the corona. Two main ideas have been put forward to explain this mystery. The first is wave heating, where waves created by turbulent motion in the layers below the photosphere, such as sound waves, gravity waves, or magnetohydrodynamic waves, travel upward into the corona and release their energy as heat. The second idea is magnetic heating, in which magnetic fields become twisted and stressed by movements in the photosphere, then suddenly snap and reconnect, releasing bursts of energy. These reconnection events can be large, such as solar flares, or very small, such as countless tiny nano flares. At present, it is not fully clear which process dominates. Most kinds of waves are thought to dissipate before reaching the corona, except for a special type called alpha waves, which are harder to dampen. Because of this, many researchers now focus on magnetic reconnection as the main heating source. The Sun itself is currently in middle age. It has been shining in its present stable state for more than 4 billion years, and will continue to do so for about another 5 billion years. After that, once the hydrogen in its core is exhausted, the Sun will change dramatically, expanding into a red giant star and eventually leaving behind a white dwarf. The Sun was born about 4.5 billion years ago from the collapse of a part of a giant cloud of gas and dust made mostly of hydrogen and helium. This cloud also gave rise to many other stars. Scientists estimate the Sun's age using models of how stars evolve, and through techniques such as nucleocosmochronology, which measures the decay of radioactive elements in ancient cosmic material. These results match very well with the ages of the oldest rocks in the solar system, which are about 4.5 billion years old. Studies of meteorites show traces of isotopes like iron-60, which can only form in exploding stars known as supernovae. This tells us that before the Sun formed, at least one nearby star must have exploded, sending out shock waves that helped trigger the collapse of the gas cloud that became our solar system. As the cloud collapsed under gravity, it also began to spin and flatten into a disk. Most of the mass collected in the center to form the Sun, while the rest spread out into a disk that later formed the planets, moons, asteroids, and comets. Even today, astronomers believe that stars such as HD 162826 and HD 186302 may be siblings of the Sun, formed from the same original cloud billions of years ago. The Sun is currently in the middle stage of its long life as a main sequence star. This is the period when nuclear fusion reactions deep inside its core steadily transform hydrogen, the lightest and most common element, into helium, the next heavier element. Incredibly, every single second, the Sun converts more than 4 billion kilograms of matter into pure energy. This tremendous process produces streams of neutrinos, tiny, almost invisible particles that rush out into space, and the powerful solar radiation that warms our world. Over its lifetime so far, the Sun has already turned into energy, the equivalent of about 100 times the total mass of planet Earth. Yet, even with all this transformation, it has used up only about 0.03% of its total mass. Scientists calculate that the Sun will remain in this main sequence stage for roughly 10 to 11 billion years before it eventually swells into a red giant star. According to findings from the European Space Agency's Gaia Space Observatory, in the year 2022, when the Sun is about 8 billion years old, it will reach the hottest point in its long life. During this main sequence period, the Sun is slowly changing. Its core grows hotter, its outer layers become hotter too, its size gradually increases, and its brightness continues to rise. Since the moment the Sun first entered this stage billions of years ago, it has expanded in size by about 15%. Its surface temperature has climbed from about 5,620 kelvins, equal to 9,660 degrees Fahrenheit, to about 5,772 kelvins, which is about 9,930 degrees Fahrenheit. Because of this, its brightness has increased by nearly half, rising from about 67% of its current light output to the full brightness we see today. The reason for this steady change lies in the fusion process itself. As hydrogen is used up in the Sun's core and replaced by helium, the helium atoms, being heavier, do not provide the same level of outward thermal pressure. This allows the core to shrink under gravity. As the inner regions contract, the outer layers fall closer to the center, releasing gravitational energy. Half of this energy heats the core even more, which speeds up fusion reactions, and in turn makes the Sun brighter and hotter. This process becomes quicker as the core continues to grow denser. At the present time, the Sun is growing brighter by about 1% every 100 million years. Scientists believe that in about 1 billion years from now, this increase in brightness will be enough to completely evaporate Earth's liquid oceans. Once that happens, Earth will no longer be able to sustain complex multicellular life. Eventually, all such life will vanish in a final mass extinction. The Sun does not have enough mass to die in a violent supernova explosion. Instead, in roughly 5 billion years, it will run out of hydrogen in its core. When that happens, fusion at the very center will stop. nothing will hold back the core from collapsing inward. The release of gravitational energy during this collapse will make the Sun's brightness surge, marking the end of its main sequence stage. Over the following billion years, the Sun will expand, first becoming a subgiant and then inflating into a massive red giant. During this phase, hydrogen fusion will restart in a thin shell around the core, adding to the Sun's increasing brightness. At its peak, it will shine more than 1,000 times brighter than today. As the Sun swells into its red giant branch, it will grow so large that it will swallow and destroy Mercury and Venus. According to research published in the year 2008, Earth's orbit will at first drift outward to about 1.5 astronomical units, or 220 million kilometers, because of the Sun's loss of mass. But later, tidal forces and friction with the Sun's extended outer layers will draw Earth inward. At the peak of the red giant phase, about 7.5 billion years from now, Earth too will be engulfed, after Mercury and Venus have already disappeared. By the end of this red giant stage, the Sun will be enormous, about 256 times its current size, with a radius of about 178 million kilometers. It will remain in this phase for around 1 billion years and lose nearly 1/3 of its total mass in the process. After the red giant branch, the Sun will only have about 120 million years of active life left. But this short span will be dramatic. Its helium-filled core will suddenly ignite in what is known as the helium flash. In just a few minutes, about 6% of the core, amounting to nearly 40% of the Sun's mass, will turn into carbon through a process called the triple alpha reaction. After this, the Sun will shrink back down to about 10 times its present size, shining about 50 times more brightly than today, though with a slightly cooler surface. It will then enter what astronomers call the red clump, or horizontal branch stage, during which it steadily burns helium in its core for about 100 million years. Once the helium runs out, the Sun will once again expand dramatically, entering the asymptotic giant branch stage. This time, it will burn hydrogen and helium in separate shells around the core, and the changes will happen much faster. After around 20 million years, the Sun will become unstable, shedding mass in bursts and undergoing powerful thermal pulses every 100,000 years. Each pulse will briefly make it swell in size and shine thousands of times brighter. Eventually it could reach up to 5,000 times its current brightness, though its maximum size at this stage will still be a little smaller than during the red giant peak. After just a handful of these thermal pulses, likely around 4, the Sun will lose its outer layers entirely. What remains will form a beautiful planetary nebula, a glowing cloud of gas surrounding the dying star. Meanwhile, the hot core will be left exposed, turning into a white dwarf star. At first, this white dwarf will be extremely hot, with a surface temperature of over 100,000 kelvins, equal to about 180,000 degrees Fahrenheit. It will contain just a little more than half of the Sun's original mass, tightly packed into a sphere about the size of Earth. The surrounding planetary nebula will slowly fade away in about 10,000 years, dispersing into space. The white dwarf itself will then cool very slowly over an unimaginably long time, lasting for trillions of years. Eventually it will fade into a cold, dark, super-dense remnant known as a black dwarf, giving off no more light or heat. The Sun has 8 officially recognized planets orbiting around it. Among these, 4 are rocky terrestrial planets: Mercury, Venus, Earth, and Mars. 2 are massive gas giants, Jupiter and Saturn, and 2 are icy giants, Uranus and Neptune. Beyond these planets, the solar system also contains at least 9 objects generally classified as dwarf planets, with several additional candidates still being studied. There is also a vast asteroid belt, countless comets, and a large population of icy objects lying far beyond Neptune's orbit. Many of these planets and smaller bodies have their own natural moons. In particular, the moon systems of Jupiter, Saturn, and Uranus are so extensive that they can, in some ways, resemble miniature versions of the entire solar system. The Sun itself is not stationary. It moves slightly in response to the gravitational pull of all the planets. The center of the Sun shifts around the solar system's barycenter, the balance point of all planetary masses, within a range of about 0.1 to 2.2 times the Sun's radius. This motion roughly repeats every 179 years, rotated by about 30 degrees, primarily due to the combined influence of Jupiter and Saturn. Most of this movement is caused by the four largest planets: Jupiter, Saturn, Uranus, and Neptune. At certain periods of several decades, when Uranus and Neptune are positioned opposite each other, the Sun's motion follows a relatively regular trefoil or clover-like pattern. At other times, it appears more chaotic. After 179 years, equivalent to 9 times the synodic period of Jupiter and Saturn, the pattern repeats again, rotated slightly by about 24 degrees. The orbits of the inner planets, including Earth, are also slightly shifted by these same gravitational forces, so the Sun's motion does not significantly affect Earth's position relative to the Sun or the amount of solar energy reaching our planet over time. The Sun's gravitational influence extends far beyond the planets. Its field dominates over the pull of nearby stars out to roughly 2 light-years, or around 125,000 astronomical units. The Oort cloud, a vast collection of icy objects at the edge of the solar system, is generally thought to extend no farther than 50,000 astronomical units. Most of the mass in the outer solar system orbits within a zone between 3,000 and 100,000 astronomical units. Some of the most distant known objects, like Comet West, have their farthest points, or Ophelia, around 70,000 astronomical units from the Sun. The Sun's Heliosphere, which is the effective range of its gravitational influence in relation to the galaxy, is calculated to reach approximately 230,000 astronomical units. Within 10 light-years of the Sun, stars are relatively sparse. The closest star system is Alpha Centauri, a triple star system about 4.4 light-years away, possibly located within a region called the local bubble's G cloud. Alpha Centauri A and B form a pair of stars similar to the Sun, while the nearest star to the Sun itself, the small red dwarf Proxima Centauri, orbits this pair at a distance of roughly 0.2 light-years. In 2016, astronomers discovered a potentially habitable planet orbiting Proxima Centauri, called Proxima Centauri b, which is the closest confirmed exoplanet to the Sun. The solar system is surrounded by a cloud of interstellar gas and dust, known as the local interstellar cloud, although it is uncertain whether the solar system lies fully inside it or just at its edge. Within a radius of roughly 300 light-years, multiple other interstellar clouds exist, forming a region called the local bubble. This bubble is shaped like an hourglass and is filled with extremely hot plasma, likely the result of several relatively recent supernovae. While the local bubble is relatively small, larger structures exist nearby, such as the Radcliffe Wave and the split linear structures, previously called the Gould Belt, each stretching for thousands of light-years. All of these structures are part of the Orion Arm, which contains most of the stars visible to the naked eye in the Milky Way. Stars often form in clusters, which gradually disperse into co-moving groups. One well-known group visible without a telescope is the Ursa Major moving group, located around 80 light-years away within the local bubble. The nearest star cluster is the Hyades, situated at the edge of the local bubble. The closest regions where new stars are forming include the Corona Australis molecular cloud, the Rho Ophiuchi cloud complex, and the Taurus molecular cloud. The latter lies just beyond the local bubble and is part of the Radcliffe Wave. Occasionally stars pass close to the Sun. Flybys within 0.8 light-years happen roughly once every 100,000 years. The closest well-documented approach was made by Schultz's star, which came within approximately 50,000 astronomical units around 70,000 years ago, likely passing through the outer part of the Oort cloud. Statistically, there is about a 1% chance every billion years that a star could pass within 100 astronomical units of the Sun, potentially disturbing the solar system. The Sun, carrying the entire solar system along with it, orbits the centre of the Milky Way galaxy at an average speed of about 230 km per second, or 828,000 km per hour. One complete orbit, called a galactic year, takes roughly 220 to 250 million Earth years. Since its formation, the Sun has completed this journey approximately 20 times. The direction of the Sun's motion, known as the solar apex, is roughly towards the star Vega. In the past, the Sun likely travelled through the Orion Eridanus superbubble before entering the local bubble. The Sun's motion relative to other stars in the galaxy is complex. In a frame of reference moving with the galaxy, the Sun travels along an elliptical path around a point that itself orbits the galactic centre. One circulation around this point takes approximately 166 million years, which is shorter than the time it takes the point to orbit the galaxy. The ellipse is about 1,760 parsecs long and 1,170 parsecs wide, compared to the Sun's distance from the galactic centre, around 7 to 8 kiloparsecs. Simultaneously, the Sun oscillates north and south of the galactic plane with a period of about 83 million years, moving roughly 99 parsecs away from the plane. The point around which the Sun circulates takes about 240 million years to complete one orbit around the galaxy. The Sun's orbit is affected by the uneven distribution of mass in the Milky Way, including the spiral arms. Some scientists suggest that as the solar system passes through denser regions of these arms, mass extinction events on Earth may be more likely due to increased asteroid and comet impacts. Each galactic orbit of the solar system takes roughly 225 to 250 million years, meaning the Sun has completed around 20 to 25 orbits during its lifetime. The orbital speed of the solar system around the Milky Way is about 251 kilometers per second. At this speed, it takes roughly 1,190 years to travel a distance of 1 light year, or about 7 days to travel the distance between the Earth and the Sun. On a larger scale, the Milky Way itself is moving relative to the cosmic microwave background radiation at a speed of about 550 kilometers per second in the direction of the constellation Hydra. Since the Sun is also moving relative to the centre of the galaxy in the direction of Cygnus at over 200 kilometers per second, its overall speed relative to the cosmic microwave background is roughly 370 kilometers per second, pointing toward the constellations Crater or Leo at a direction about 132 degrees away from Cygnus. For countless prehistoric and ancient cultures across the world, the Sun was much more than a bright object in the sky. It was often seen as a god, a divine being, or some form of supernatural presence. People revered it, feared it, and sometimes even built elaborate myths and rituals around it. By the early first millennium before the Common Era, Babylonian astronomers had begun to notice something puzzling. The Sun did not move evenly across the sky along the path we now call the ecliptic. They could not explain why this happened, but today we know that the apparent irregular motion of the Sun is a consequence of Earth's elliptical orbit, moving faster when it is closest to the Sun at perihelion and slower when it is farthest away at aphelion. One of the earliest thinkers to offer a more scientific or philosophical explanation was the Greek philosopher Anaxagoras. He suggested that the Sun was not a god but a gigantic flaming sphere of metal, even larger than the entire Peloponnesus Peninsula, and that the Moon shone merely because it reflected the Sun's light. Later, in the 3rd century before the Common Era, the Greek scholar Eratosthenes attempted to measure the distance from Earth to the Sun. He gave a figure expressed as of stadia myriads 480,000, which is ambiguous in modern terms. Depending on the interpretation, it could mean 4,080,000 stadia, roughly 755,000 kilometers, or 804 million stadia, about 148 to 153 million kilometers, almost exactly one astronomical unit. The latter is remarkably close to the true distance. A few centuries later, in the 1st century of the Common Era, the astronomer Ptolemy estimated the distance as 1,210 times the radius of Earth, or approximately 7,710,000 kilometers. The revolutionary idea that the Sun, not the Earth, lies at the centre of the planetary system was first proposed by the Greek astronomer Aristarchus of Samos in the 3rd century before the Common Era. This heliocentric concept was later supported by Seleucus of Seleucia, and many centuries afterward was mathematically refined into a full heliocentric model by the 16th century astronomer Nicolaus Copernicus. Records of sunspots, the dark patches visible on the Sun's surface, go back to ancient China during the Han Dynasty, from 202 before the Common Era to 220 in the Common Era. These observations were carefully maintained for centuries. In the 12th century, the philosopher and astronomer Averroes also described sunspots. With the invention of the telescope in the early 17th century, detailed studies of sunspots became possible, with astronomers like Thomas Harriot and Galileo Galilei observing them closely. Galileo famously concluded that these spots were features on the Sun itself, rather than small objects passing between the Sun and Earth. Medieval Islamic scholars also made important contributions. Al-Battani discovered that the Sun's apogee, the point in its apparent orbit where it seems to move most slowly against the backdrop of stars, changes over time. Today, we understand this as the gradual motion of Earth's aphelion. Another scholar, Ibn Yunus, meticulously recorded over 10,000 entries of the Sun's position using a large astrolabe over many years. The first reasonably accurate measurement of the Earth-Sun distance came in 1684 through the work of Giovanni Domenico Cassini. Because direct measurements of the Sun's parallax were extremely difficult, Cassini cleverly measured the parallax of Mars instead. He sent Jean Richet to Cayenne, in what is now French Guiana, to take simultaneous measurements while he observed from Paris. From the difference in the observed positions and using Kepler's laws, Cassini calculated the distance to Mars and then deduced the distance to the Sun. His result, while about 10% smaller than the modern value, was far larger and more accurate than any previous estimate. Astronomers had also used planetary transits to infer relative distances. In the year 1032, the Persian polymath Ibn Sina observed a transit of Venus and concluded that Venus must be closer to Earth than the Sun. Later, in 1677, Edmund Halley studied a transit of Mercury across the Sun and realized that measuring such transits could help determine the distances from Earth to Venus and from Earth to the Sun. By carefully observing the transit of Venus in 1769, astronomers calculated the average Earth-Sun distance to be 93,726,900 miles, or roughly 150,838,800 kilometers, a value only about 0.8% larger than today's accepted distance. In the 17th century, Isaac Newton used a prism to study sunlight in 1666, and discovered that it is composed of many colours. In 1800, William Herschel found infrared radiation beyond the red end of the spectrum. The 19th century saw major advances in solar spectroscopy. Joseph von Fraunhofer recorded over 600 dark lines in the solar spectrum, the strongest of which are still known as Fraunhofer lines. By the 20th century, astronomers were able to observe the Sun in highly specific wavelengths, such as those filtered for calcium H, calcium K, and hydrogen alpha light. During early spectroscopic studies, some absorption lines were observed that did not match any known chemical elements on Earth. In 1868, Norman Lockyer proposed that these lines were caused by a new element, which he named helium after the Greek sun god Helios. It would be 25 years before helium was finally isolated on Earth. Understanding the source of the Sun's energy was a major puzzle in the early modern scientific era. Lord Kelvin suggested that the Sun was a gradually cooling body radiating stored heat. He, along with Hermann von Helmholtz, proposed that gravitational contraction could supply the Sun's energy, but this yielded an age of only 20 million years, far shorter than the minimum 300 million years indicated by geological evidence. In 1890, Lockyer suggested that the Sun formed and evolved through the accumulation of meteoritic material. A clear scientific explanation emerged only in 1904, when Ernest Rutherford proposed that radioactive decay could provide an internal source of heat. However, the crucial breakthrough came from Albert Einstein, whose famous mass-energy equivalence formula, E equals mc squared, revealed how mass could be converted into energy. In 1920, Sir Arthur Eddington proposed that the extreme pressures and temperatures at the Sun's core could trigger nuclear fusion, combining hydrogen nuclei into helium and releasing energy in the process. Cecilia Payne confirmed in 1925 that hydrogen is the dominant element in the Sun, using the ionization theory of Meghnad Saha. In the 1930s, astrophysicists Subrahmanyan Chandrasekhar and Hans Bethe developed the detailed theory of nuclear fusion in stars, with Bethe calculating the two main reactions that power the Sun. Finally, in 1957, Margaret Burbidge, Geoffrey Burbidge, William Fowler, and Fred Hoyle demonstrated that nearly all elements in the universe are formed through nuclear reactions in stars like our Sun. The first spacecraft specifically built to observe the Sun over long periods from space beyond Earth's atmosphere were the Pioneer series, Pioneer 6, 7, 8, and 9. These probes were launched by NASA between the years 1959 and 1968. They travelled around the Sun at roughly the same distance as Earth, and were the first to provide detailed measurements of the solar wind, the stream of charged particles constantly flowing from the Sun and the Sun's magnetic field. Among them, Pioneer 9 had an exceptionally long mission, continuing to send data back to Earth until May 1983. During the 1970s, scientists gained even more insight into the Sun through the Helios spacecraft and the Skylab space station's Apollo telescope mount. The Helios 1 and 2 missions, a collaboration between the United States and Germany, studied the solar wind from orbits that took the spacecraft closer to the Sun than Mercury at their nearest approach, known as perihelion. Meanwhile, Skylab, launched by NASA in 1973, carried the Apollo telescope mount, a solar observatory that astronauts on the station could operate directly. Through this observatory, scientists made the first detailed, time-resolved observations of the Sun's transition region, the thin layer between the Sun's surface and corona, and measured ultraviolet emissions from the solar corona. Skylab also revealed phenomena that were previously unknown, including the first observations of coronal mass ejections, which at the time were called coronal transients and coronal holes, areas now known to be closely linked with the solar wind. In 1980, NASA launched the Solar Maximum mission to study high-energy events on the Sun, such as solar flares, by observing gamma rays, X-rays, and ultraviolet light during periods of maximum solar activity. Unfortunately, just a few months after launch, an electronics failure put the spacecraft into standby mode, where it remained inactive for 3 years. In 1984, the Space Shuttle Challenger mission, STS-41C, retrieved the satellite, repaired its electronics, and returned it to orbit. After this repair, the Solar Maximum mission captured thousands of images of the solar corona before finally re-entering Earth's atmosphere in June 1989. Japan contributed to solar observation with the Yohkoh satellite, whose name means sunbeam, launched in 1991. Yohkoh studied solar flares in X-ray wavelengths, allowing scientists to classify different types of flares and showing that the solar corona was far more dynamic and active even outside the most energetic regions than had been previously thought. Yohkoh observed the Sun for an entire solar cycle, but went into standby mode in 2001 during an annular solar eclipse when it lost its lock on the Sun. It eventually burned up during re-entry into Earth's atmosphere in 2005. The Solar and Heliospheric Observatory, or SOHO, is a joint mission by the European Space Agency and NASA, launched on the 2nd of December 1995. Initially planned as a 2-year mission, SOHO remains active as of 2024. Positioned at a Lagrangian point between Earth and the Sun, where the gravitational forces of both bodies balance, SOHO has provided an uninterrupted view of the Sun in multiple wavelengths. Beyond its primary role in observing the Sun, SOHO has helped discover hundreds of comets, mostly small sun-grazing comets that burn up as they approach the Sun. All of these spacecraft mainly observed the Sun from the plane of Earth's orbit, called the ecliptic, meaning they focused on the Sun's equatorial regions. To study the Sun's polar regions, the Ulysses probe was launched in 1990. Ulysses first travelled to Jupiter, using the planet's gravity as a slingshot to reach an orbit taking it far above the ecliptic plane. Once in its final orbit, Ulysses measured the solar wind and magnetic field at high latitudes, finding that solar wind from these regions travelled at around 750 km per second, slower than expected, and that large magnetic waves from high latitudes scattered galactic cosmic rays. While scientists have a strong understanding of the Sun's outer layer, the photosphere, through spectroscopy, the composition of the Sun's interior is less certain. The Genesis mission was designed to bring back samples of the solar wind so that astronomers could directly measure the Sun's material. The Sun is extremely bright, and staring at it with the naked eye can cause discomfort or even damage. Brief glances are usually not harmful for normal, non-dilated eyes, but prolonged viewing, known as sungazing, can produce temporary visual effects called phosphonies, partial blindness, and even heat-induced damage to the retina. Direct viewing delivers about 4 milliwatts of sunlight to the retina, enough to potentially cause harm in eyes that cannot adjust properly to brightness. Exposure for around 100 seconds under intense ultraviolet light can produce lesions on the retina similar to sunburn. Looking at the Sun through optical devices such as binoculars or telescopes without proper solar filters can cause permanent eye damage, as these devices concentrate sunlight and ultraviolet rays. Only filters specifically designed to block dangerous rays should be used, as improvised solutions may fail and even worsen the damage. Even short, unfiltered glimpses through a telescope at midday can permanently harm the eyes. However, the Sun is sometimes safer to view during sunrise or sunset, when its light passes through more of Earth's atmosphere. Scattering of light by air molecules and particles, known as Rayleigh and Mie scattering, reduces the Sun's brightness. Hazy weather, dust and high humidity further dim sunlight, making it easier to observe safely. A rare optical effect called a green flash can sometimes be seen just after sunset or before sunrise. This occurs when the sun is just below the horizon, and its light is bent by temperature inversions in the atmosphere. Shorter wavelengths of light, like violet, blue, and green, are bent more than longer ones, but violet and blue are scattered away, leaving a brief green flash visible to the observer. WOHG 64 is a fascinating symbiotic binary star system located in the Large Magellanic Cloud, approximately 160,000 light-years from Earth. The primary star in this system was once celebrated as the best candidate for the largest known star when it shone as a red supergiant. Over time, however, it has undergone dramatic changes, transforming into a yellow hypergiant roughly half the size of its former self. The secondary star is a B-type star, and the system as a whole exhibits features reminiscent of B stars, a rare and peculiar class of stars surrounded by hot, ionized gas. Surrounding WOHG 64 is a dense and optically thick envelope of dust, stretching nearly a light-year across. This dusty cocoon contains between 3 and 9 times the mass of our Sun, material expelled over time by the star's intense stellar wind. The star was first discovered in the 1970s by Bengt Westerlund, Niels Orlander, and Bengt Hedin. The name WOHG comes from the initials of these 3 astronomers and refers to a catalogue of giant and supergiant stars within the Large Magellanic Cloud. Westerlund also identified another remarkable red supergiant, Westerlund 1-26, located within the massive superstar cluster Westerlund 1 in the constellation Ara. By 1986, infrared observations revealed WOHG 64 as an extremely luminous supergiant, cloaked in gas and dust that absorbed roughly 3/4 of its emitted radiation. In 2007, the Very Large Telescope provided evidence that WOHG 64 is encircled by a torus-shaped cloud of dust. 17 years later, in 2024, the dusty torus was directly imaged by the Very Large Telescope Interferometer, revealing a compact, elongated emission surrounding the hypergiant. This marked the first time a star outside the Milky Way had been captured through interferometric imaging. During its red supergiant phase, WOHG 64 displayed regular variations in brightness, exceeding 1 magnitude at visual wavelengths, with a primary period of roughly 800 days. However, its brightness in infrared light varied much less, due to more than 6 magnitudes of extinction at visible wavelengths caused by surrounding dust. While it has been described as a carbon-rich mirror or long-period variable, typically an asymptotic giant branch star rather than a supergiant, its exact variability type remains unclear. Today, it is classified as an irregular variable star. Spectral measurements indicate that WOHG 64a, in its red supergiant phase, had a spectral type around M5, though it is more commonly observed as M7.5, which is unusually cool for a supergiant. At this stage, it was likely the largest, most luminous and coolest red supergiant in the Large Magellanic Cloud. Its combination of extreme size and brightness placed it near the upper right corner of the Hertzsprung-Russell diagram, with an extraordinary mass loss rate between 3.1 and 5.8 times 10 to the -4 solar masses per year, among the highest ever recorded. Early calculations based on spherical models of the star's surrounding shells estimated WOHG 64's luminosity to be between 490,000 and 600,000 times that of the Sun, implying an initial mass of at least 40 solar masses and a radius between 2,575 and 3,000 times that of the Sun. Later measurements in 2018 suggested a luminosity of 432,000 solar luminosities and an effective surface temperature of 3,500 Kelvin, giving a radius of 1,788 solar radii. However, observations in 2007 revealed the dust around WOHG 64 has a torus-like shape seen almost directly from above. This means earlier estimates assuming spherical shells were too high. Radiative transfer models of the torus suggested a lower luminosity of roughly 282,000 solar luminosities, an initial mass of 25 plus or minus 5 solar masses, and a radius of approximately 1,730 solar radii at an effective temperature of 3,200 Kelvin. Subsequent spectral fitting in 2009 by Emily Levesque calculated a temperature of 3,400 plus or minus 25 Kelvin, which implies a radius of roughly 1,540 solar radii, comparable to the largest red supergiants and hypergiants found in the Milky Way, such as Canis Majoris, and consistent with theoretical limits for the coolest, largest supergiants. WOHG 64 is also an active source of OH, H2O, and SiO masers, typical of an OHIR supergiant. Its spectrum shows unusual nebular emission rich in nitrogen, with gas moving at a higher radial velocity than the star itself. The stellar atmosphere produces strong silicate absorption in mid-infrared wavelengths, along with emission lines from highly excited carbon monoxide. Since 2014, WOHG 64 has continued to evolve, shrinking into a smaller yellow hypergiant about 800 times the Sun's radius, roughly half its former size, and transitioning from semi-regular to irregular variability. A preprint in 2024 confirmed that WOHG 64 is a symbiotic star, with a smaller B-type companion drawing material from the hypergiant. Since 2016, spectral observations show features of both B stars and yellow stars, consistent with a massive symbiotic binary system, a yellow hypergiant losing material to a B-type star companion, the persistent surrounding hot dust, the elongated appearance in interferometric images, and the lack of any violent outburst during the transition from red supergiant all support this binary nature. WOHG 64's behavior is analogous to the interacting binary system HR 5171, which also contains a yellow hypergiant paired with a B-type companion. The presence of a hot stellar companion was first suggested in 2009, when it was proposed that a late O-type main sequence star could be ionizing the nebula around WOHG 64, explaining the 50 km per second shift between nebular emission lines and the star's spectral features. Betelgeuse is a magnificent red supergiant star that graces the constellation of Orion. In the night sky, it usually ranks as the 10th brightest star visible to the naked eye and, within its own constellation, is second only to Rigel in brilliance. Its colour is a vivid reddish-orange, making it easily distinguishable, and it is classified as a semi-regular variable star. This means its brightness gently fluctuates over time. Its apparent magnitude, a measure of how bright it looks from Earth, varies between 0.0 and 1.6, with a primary cycle lasting roughly 400 days. Among all stars of first magnitude, Betelgeuse exhibits the widest range of brightness. Interestingly, when observed in near-infrared wavelengths, it is the brightest star in the night sky. Its official Bayer designation is Alpha Orionis, often abbreviated as Alpha Ori. Betelgeuse is enormous. Its radius is estimated to be between 640 and 764 times that of our Sun. To put this in perspective, if Betelgeuse were placed at the centre of our solar system, its surface would extend well beyond the asteroid belt, swallowing the orbits of Mercury, Venus, Earth and Mars. Its mass is estimated to be somewhere between slightly under 10 times and just over 20 times that of the Sun. Determining its exact distance has been a challenge for astronomers. The best current estimates place it between 400 and 600 light-years from Earth, a surprisingly wide uncertainty for a relatively nearby star. Betelgeuse shines with an absolute magnitude of about -6, a measure of its intrinsic brightness. Despite being less than 10 million years old, it has evolved rapidly because of its massive size. Eventually, Betelgeuse is expected to end its life in a spectacular supernova explosion, likely within 100,000 years. When it does explode, it could shine as brightly as the half-moon for over 3 months, yet life on Earth would remain unharmed. Once part of the Orion OB1 association, a stellar nursery that includes the famous stars of Orion's belt, Betelgeuse is now a runaway star, moving through the interstellar medium at about 30 km per second. Its rapid motion creates a vast bow shock over 4 light-years wide. In 1920, Betelgeuse became the first star beyond the Sun whose photosphere, the visible surface, was measured in angular size. Later studies reported its apparent diameter ranging from 0.042 to 0.056 arc-seconds. These variations are due to the star's non-spherical shape, limb darkening, pulsations, and changes in appearance across different wavelengths. Surrounding Betelgeuse is a complex, uneven envelope roughly 250 times its size, formed by material ejected from the star itself. From Earth, only the Sun and the star R Doradus appear larger in angular diameter. In October of 2019, Betelgeuse began to dim noticeably. By mid-February of 2020, its brightness had dropped by roughly a factor of 3, going from a magnitude of 0.5 to 1.7. By April of 2023, it returned to a normal brightness, peaking at 0.0 in visual magnitude. Infrared observations over the past 50 years show no significant change in the star's overall luminosity, suggesting the dimming was caused not by a fundamental change in the star itself, but by material, dust, blocking its light. Observations with the Hubble Space Telescope indicate this dust originated from a surface mass ejection, with the expelled matter travelling millions of miles before cooling and forming the obscuring dust. There is some evidence, though unconfirmed, that Betelgeuse may have a companion star. Known as Betelgeuse b or Siwara, this companion is thought to be much smaller and fainter, orbiting at a distance just a few times the size of Betelgeuse itself. In 2016, the International Astronomical Union established the Working Group on Star Names to catalogue and standardise proper star names. Their first bulletin, issued in July of that year, included Betelgeuse, now officially recorded in the IAU catalogue of star names. The companion star's proposed name, Siwaha, meaning her bracelet in Arabic, was officially recognised on the 22nd of September 2025. The fiery red colour of Betelgeuse has been noted for millennia. The classical astronomer Ptolemy described its hue as hyperkairos, roughly orange tawny, which later translators of Ulugh Beg's Zigi Sultani rendered as rubedo, Latin for ruddiness. In the 19th century, before modern stellar classifications, Angelo Secchi used Betelgeuse as a prototype for his Class 3 stars, characterized by orange to red coloration. Interestingly, Chinese astronomers observed it as yellow some 3 centuries before Ptolemy, suggesting that Betelgeuse may have been a yellow supergiant at that time, consistent with modern research into the complex environment around massive stars. Aboriginal peoples in South Australia have long shared oral traditions noting the star's variable brightness. The star's fluctuations in brightness were formally recorded by Sir John Herschel in his Outlines of Astronomy in 1836. Between 1836 and 1840, he noted remarkable changes, with Betelgeuse outshining Rigel in October of 1837 and again in November of 1839. A quiet period followed. Then in 1849, Herschel observed another brief cycle peaking in 1852. Subsequent observers documented unusually high maxima over years, though only minor variations were seen between 1957 and 1967. Records from the American Association of Variable Star Observers show a maximum brightness of 0.2 in 1933 and 1942, and a minimum of 1.2 in 1927 and 1941. These brightness variations likely explain why Johann Bayer, in his Uranometria of 1603, designated the star Alpha, as it often rivaled Rigel in brightness. From Arctic regions, Betelgeuse's red colour and higher position in the sky led the Inuit to regard it as the brighter star, giving it the name Ulurejwak, meaning large star. In 1920, Albert A. Michelson and Francis G. Pease, assisted by John August Anderson, used a 6-metre interferometer on the front of the 2.5-metre telescope at Mount Wilson Observatory to measure Betelgeuse's angular diameter at 0.047 arc-seconds. This implied a diameter of 384 million kilometres, or about 2.58 astronomical units. Measurement uncertainties, however, arose from limb darkening and other technical limitations. In the 1950s and 1960s, 2 major developments advanced our understanding of convection in red supergiants. The stratoscope projects, which used balloon-borne telescopes to rise above Earth's turbulent atmosphere, produced exceptionally clear images of solar granules and sunspots, confirming convection in the Sun's atmosphere. Meanwhile, the 1958 publication Structure and Evolution of the Stars by Martin Schwarzschild and Richard Herm introduced the application of computer modelling to the study of stellar interiors, shaping modern theories of massive star evolution. During the 1970s, astronomers experienced remarkable progress in the tools and methods used to observe stars. A key breakthrough came from French astronomer Antoine Laberry, who developed speckle interferometry, a clever technique that greatly reduced the blurring caused by Earth's atmosphere, often called astronomical seeing. This method allowed ground-based telescopes to achieve much sharper images, giving astronomers far more precise views of Betelgeuse's outer layer, known as the photosphere. Around the same period, advances in infrared telescopes atop mountains like Mount Wilson, Mount Locke, and Mauna Kea in Hawaii opened a window into the complex layers of gas surrounding the star. These observations hinted at enormous convection-driven gas bubbles, showing that Betelgeuse's environment was far more dynamic than previously imagined. The real leaps in imaging came in the late 1980s and early 1990s, when Betelgeuse became a frequent target for aperture masking interferometry. Developed by J.E. Baldwin and his team at the Cavendish Astrophysics Group, this method involved placing a small mask with multiple holes in the telescope's light path, effectively transforming the telescope into a temporary interferometer. Using this technique, astronomers captured some of the most accurate measurements of Betelgeuse and discovered bright regions on its surface, hotspots, providing the first detailed optical and infrared images of a star's disk apart from the Sun. These bright patches confirmed a theory first suggested decades earlier by Martin Schwarzschild, who proposed that massive convection cells dominated the star's surface. In 1995, the Hubble Space Telescope, using its faint object camera, captured an ultraviolet image of Betelgeuse with resolution surpassing what ground-based interferometers could achieve. This became the first direct image of another star's disk using conventional telescope methods. Ultraviolet light is mostly blocked by Earth's atmosphere, so space telescopes are essential for such observations. The image revealed a bright spot in the star's southwestern quadrant, about 2000 kelvins hotter than the surrounding surface. Later, ultraviolet spectra from Hubble's Goddard high-resolution spectrograph suggested that this bright spot marked one of Betelgeuse's rotational poles, placing the star's rotational axis at an inclination of roughly 20 degrees toward Earth and at a position angle from celestial north of approximately 55 degrees. By December 1999, astronomers measured the star's diameter using the Infrared Spatial Interferometer, ISI, at mid-infrared wavelengths. They estimated a limb-darkened diameter of 55.2 plus 0.5 milliseconds, remarkably consistent with measurements made by Michelson about 80 years earlier. At that time, data from the Hipparcos mission suggested a parallax of 7.63, plul 1.64 milliseconds, implying a radius of roughly 3.6 astronomical units for Betelgeuse. However, a 2009 infrared study suggested that the star had shrunk by 15% since 1993, though its overall brightness had not decreased significantly. Later observations indicate that this apparent contraction might be linked to activity in the star's extended shell. Astronomers have also explored the complex dynamics of Betelgeuse's atmosphere, especially its mass loss, which is critical for understanding how stars recycle matter into galaxies. Red supergiants like Betelgeuse shed enormous amounts of mass, but exactly how this happens remains uncertain. Groundbreaking interferometric images released by the European Southern Observatory in July 2009, taken by the Very Large Telescope Interferometer, revealed a massive gas plume extending 30 astronomical units from the star, roughly the distance from the Sun to Neptune. Multiple shells of gas and dust surround Betelgeuse, at least 6 in total, each contributing to its complex and evolving atmosphere. Understanding these processes could help scientists predict how such stars eventually end their lives in spectacular supernova explosions. Betelgeuse is a semi-regular variable star, meaning its brightness changes over time due to shifts in size and temperature. In the Great Dimming of 2020, astronomers including Richard Wassertonic, Edward Guinan, and amateur observer Thomas Calderwood suggested that the dimming was caused by a rare alignment of Betelgeuse's normal 5.9-year cycle with a deeper than usual 425-day cycle, though other explanations included surface eruptions of gas or dust. By August 2020, extensive studies using Hubble Space Telescope ultraviolet data indicated that the dimming was most likely caused by a huge amount of superheated material ejected from the star. This material cooled and formed a dust cloud that blocked light from about a quarter of the star's surface. Observations through September, October, and November captured dense, heated gas moving through the atmosphere, followed by noticeable dimming in December and the first months of 2020. By January 2020, Betelgeuse's brightness had dropped from magnitude 0.5 to 1.5, representing a reduction in luminosity by a factor of about 2.5. In February, the star reached a record minimum of magnitude 1.614, becoming the least luminous and coolest observed in the past 25 years. This event caused Betelgeuse to drop from the top 10 brightest stars to outside the top 20, noticeably dimmer than nearby Aldebaran. While some media speculated a supernova was imminent, astronomers clarified that such an explosion is expected within roughly 100,000 years, making it extremely unlikely to happen soon. By 17th February 2020, Betelgeuse's brightness had stabilized, and signs of rebrightening appeared. On 22nd February, the star may have stopped dimming entirely, effectively ending the dimming episode. Infrared studies on 24th February suggested no major change over the last 50 years, implying the fading was likely unrelated to an impending core collapse. Observations pointed to circumstellar dust or large star spots as the primary causes of the temporary dimming. A follow-up study on 31st March 2020 recorded a rapid increase in brightness. Betelgeuse is nearly impossible to observe from Earth between May and August due to its proximity to the Sun. Before its 2020 solar conjunction, the star reached magnitude 0.4. Observations from the Stereo A spacecraft in June and July revealed a dimming of 0.5 magnitude since April, earlier than expected. By 31st August 2020, astronomers detected a second dust cloud, likely responsible for a secondary dimming event on 3rd August. In June 2021, researchers suggested the dust may have formed from a cool patch on Betelgeuse's photosphere, later confirmed by another team in August 2021. Gas ejected from the star cooled, creating the dust. Observations in August 2022 by Hubble supported this, proposing that a surface mass ejection triggered the dimming. The event might have coincided with both a short-term 416-day cycle and a long-term 2010-day cycle, forming a grand minimum, a mechanism first suggested by astronomer L. Goldberg. By April 2023, Betelgeuse had brightened again, reaching magnitude 0.0 in visual and 0.1 in the V-band. This remarkable series of events is often called the Great Dimming, a stunning reminder that even familiar stars in our night sky continue to surprise and challenge astronomers. Betelgeuse, with its striking orange-red glow and prominent location in the constellation of Orion, is one of the easiest stars to spot in the night sky with the naked eye. Its radiant colour immediately catches attention, even among the countless other stars. Betelgeuse is also a key member of several famous stellar patterns. It forms one of the 3 points of the winter triangle, and it sits at the heart of the winter hexagon, a vast star pattern visible in the colder months. Each year, Betelgeuse rises in the eastern sky around the beginning of January, shortly after the sun sets. From mid-September to mid-March, with the best visibility around mid-December, it can be seen from almost every inhabited part of Earth, except in the icy reaches of Antarctica beyond 82 degrees south latitude. In the spring and early summer months, around May for moderate northern latitudes or June for southern latitudes, the star appears briefly on the western horizon after sunset, only to re-emerge several months later in the eastern sky before sunrise. During the months of June to July, centered around mid-June, Betelgeuse becomes nearly invisible to the naked eye, visible only through telescopes during the daytime, except in Antarctica between 70 and 80 degrees south latitude, where it may be seen low in the northern sky during midday twilight under polar night conditions, when the sun remains below the horizon. Betelgeuse is a variable star, meaning its brightness changes over time. Its visual magnitude fluctuates between 0.0 and plus 1.6. There are periods when Betelgeuse outshines Rigel, briefly becoming the 6th brightest star in the sky, and occasionally it can even surpass Capella in brilliance. At its dimmest, it falls behind stars like Deneb and Beta Crucis, both of which also vary slightly in brightness, making Betelgeuse only the 20th brightest star. The star's BV colour index is 1.85, highlighting its intense red hue. Its outer layer, or photosphere, is enveloped by a vast extended atmosphere that behaves unusually. Instead of the typical absorption lines seen in most stars, Betelgeuse shows strong emission lines. This phenomenon occurs because the star is surrounded by a thick gaseous envelope, rather than a simple ionized atmosphere. Observations reveal that this gas sometimes flows toward the star, and at other times moves away, influenced by fluctuations in the photosphere. Interestingly, Betelgeuse is the brightest source in the sky in the near-infrared spectrum, with a J-band magnitude of -2.99, yet only about 13% of its energy is emitted as visible light. Were human eyes sensitive to all wavelengths, Betelgeuse would appear as the brightest star in the entire night sky. Astronomical catalogues also list up to 9 faint visual companions to Betelgeuse, all located roughly 1 to 4 arc-minutes away, each dimmer than the 10th magnitude, making them challenging to see without telescopes. Understanding the distance to Betelgeuse has been a long-standing puzzle in astronomy. The key method for measuring stellar distances is parallax, the apparent shift in a star's position against the background as Earth orbits the Sun. This tiny angular shift, measured in seconds of arc, combined with the known size of Earth's orbital path, allows astronomers to calculate a star's distance. The first successful stellar parallax measurement was achieved by Friedrich Bessel in 1838, but Betelgeuse's distance remained uncertain for many decades. Accurate distance measurements are crucial because they help determine other fundamental properties of the star, such as its luminosity, radius, effective temperature, mass, and age. In 1920, the first interferometric studies of Betelgeuse's diameter assumed a parallax of 0.018 seconds of arc, translating to a distance of 56 parsecs, or roughly 180 light-years. This early estimate produced inaccurate calculations for the star's size and all other characteristics. Over the years, estimates ranged as high as 400 parsecs, or about 1,300 light-years, reflecting the difficulty of precise measurements. Before the Hipparcos catalogue was published in 1997, 2 slightly conflicting parallax values existed. One in 1991 measured 9.8 plus or minus 4.7 milliseconds, giving a distance of approximately 102 parsecs or 330 light-years. The other, from the Hipparcos input catalogue in 1993, suggested 5 plus or minus 4 milliseconds, a distance of about 200 parsecs or 650 light-years. When Hipparcos data was released in 1997, it showed a parallax of 7.63 plus or minus 1.64 milliseconds, equating to roughly 131 parsecs or 427 light-years, with smaller error than previous measurements. Later evaluations revealed that the uncertainties for variable stars like Betelgeuse had been underestimated. In 2007, a refined parallax of 6.55 plus or minus 0.83 milliseconds gave a more precise distance of roughly 152 plus or minus 20 parsecs, or 500 plus or minus 65 light-years. Radio measurements with the Very Large Array in 2008 suggested a parallax of 5.07 plus or minus 1.10 milliseconds, equaling a distance of 197 plus or minus 45 parsecs, or 643 plus or minus 146 light-years. Combining multiple datasets, astronomer Harper noted that systematic errors remained, though the combined solution reduced some uncertainties. More recent observations using ALMA and E. Merlin yielded a parallax of 4.51 plus or minus 0.8 milliseconds, corresponding to a distance of 222 plus 34 minus 48 parsecs, or roughly 724 plus 111 minus 156 light-years. In 2020, data from the space-based Solar Mass Ejection Imager aboard the Coriolis satellite, using 3 modelling methods, produced a refined parallax of 5.95 plus 0.58 minus 0.8 milliseconds, a radius of 764 plus 116 minus 62 solar radii, and a distance of 168.1 plus 27.5 minus 14.4 parsecs, or 548 plus 90 minus 49 light-years, suggesting Betelgeuse is about 25% smaller and closer than previously thought. A study in 2022 suggests Betelgeuse is even smaller and closer, based on historical records showing the star's colour change from yellow to red over the last 1,000 years. This indicates a mass of 14 solar masses, much lower than earlier estimates, with a best-fit evolutionary track suggesting a distance of about 125 parsecs, or 410 light-years, consistent with Hipparcos data. The European Space Agency's Gaia mission cannot reliably measure parallax for stars as bright as Betelgeuse which exceeds the mission's instrument limit of approximately magnitude 6. Consequently, no Gaia parallax data is available for Betelgeuse in either Data Release 2 of 2018 or Data Release 3 of 2022. Betelgeuse is known as a semi-regular variable star, which means its brightness changes in a way that has some pattern, but is not perfectly consistent. Its variations can differ in intensity. The time between peaks can shift, and there may be periods when the brightness barely changes or behaves irregularly. Astronomers place it in a subgroup called SRC, which includes red supergiant stars that pulse with brightness changes of roughly 1 magnitude, and whose cycles can last anywhere from a few tens of days to several hundreds of days. Typically, Betelgeuse hovers around a brightness of magnitude plus 0.5, but at its brightest it can reach magnitude 0, and at its faintest it can drop to magnitude plus 1.6. The star is included in the General Catalogue of Variable Stars, which lists a possible period of 2,335 days. More detailed studies have revealed a primary period close to 400 days, a shorter period of 185 days, and a longer secondary cycle of about 2,100 days. The dimmest reliably recorded brightness in the V-band was magnitude plus 1.614, noted in February 2020. The pulsations of red supergiants like Betelgeuse are reasonably well understood. Periods lasting a few hundred days are typically caused by fundamental and first overtone pulsations, which are essentially rhythmic expansions and contractions of the star. Spectral studies reveal tiny Doppler shifts in Betelgeuse's light, indicating changes in its radial velocity that roughly correspond to its brightness variations. This confirms that the star physically expands and contracts, although changes in its temperature and spectrum are less clear. Astronomers have even measured changes in the star's diameter directly. The shorter, 185-day pulsations provide important clues about the star's internal structure and age, as the ratio between the fundamental and overtone periods can reveal details of its inner workings. The longer secondary periods, however, remain a mystery, as they cannot be explained by simple radial pulsation. Observations using interferometry have revealed hotspots on Betelgeuse's surface, likely caused by massive convection cells. These cells are enormous, covering a significant fraction of the star's surface and emitting between 5 and 10% of its total light. Some scientists suggest that long secondary periods may result from the evolution of these cells combined with the star's rotation. Other theories propose effects from a close binary companion, magnetic activity influencing mass loss, or non-radial pulsations such as G-modes. Beyond these main pulsation cycles, Betelgeuse shows smaller, random variations in brightness. These are thought to arise from granulation, similar to the surface bubbling seen on the Sun but on a much larger scale. Historically, Betelgeuse made astronomy history on the 13th of December, 1920, when it became the first star outside our solar system to have the angular size of its visible surface measured. Although interferometry was still very new at the time, the experiment succeeded. Researchers using a simple uniform disk model calculated an angular diameter of 0.047 arcseconds, which, after correcting for limb darkening, likely represented an angular diameter of about 0.055 arcseconds. Subsequent studies have measured diameters ranging from 0.042 to 0.069 arcseconds. Combining these measurements with historical distance estimates from 180 to 815 light-years yields a projected radius anywhere from 1.2 to 8.9 astronomical units. To put this in perspective, Mars orbits at about 1.5 AU, the dwarf planet Ceres at 2.7 AU, and Jupiter at 5.5 AU. This means that if Betelgeuse replaced the Sun, its surface would extend just past the orbit of Jupiter, but fall short of Saturn at 9.5 AU. Astronomers often refer to the Rossellin radius when discussing large cool stars. This is the radius of the star's visible surface at a specific optical depth, calculated from the star's temperature and total brightness. Directly measured radii differ slightly due to limb darkening and observational wavelength. For instance, a measured angular diameter of 55.6 milliseconds corresponds to a Rossellin mean diameter of 56.2 milliseconds, while including surrounding dust and gas reduces it to 41.9 milliseconds. To improve the accuracy of measurements, astronomers have relied on interferometry, first proposed by Hippolyte Fizeau in 1868. Fizeau suggested observing stars through 2 apertures instead of 1 to to produce interference patterns that reveal details about the star's shape and surface brightness. This principle was further developed into the Michelson interferometer in the 1880s and eventually led to the first successful measurement of Betelgeuse's size. Modern techniques involve multiple aperture interferometers, which combine light from several telescopes and process it using Fourier analysis to produce high-resolution images. It was this method in the 1990s that uncovered the surface hotspots of Betelgeuse. Other technological advancements such as adaptive optics and space telescopes like Hipparcos, Hubble and Spitzer, along with instruments like the Astronomical Multibeam Recombiner, have allowed astronomers to measure details on scales as small as milliarc seconds. Different observational wavelengths yield different measurements. In 1996, Betelgeuse appeared as a uniform disk with a diameter of 56.6 milliarc seconds. By the year 2000, a team measured a diameter of 54.7 milliarc seconds, not accounting for hotspots, and adjusted for limb darkening, this became 55.2 milliarc seconds. Assuming a distance of 197 parsecs, this corresponds to a radius of roughly 5.6 AU, close to Jupiter's orbit. Near-infrared studies in 2004 gave a more precise photospheric diameter of 43.33 milliarc seconds. Differences in diameter at different wavelengths are explained by the star's thick, warm extended atmosphere. At visible wavelengths, scattered light slightly enlarges the apparent diameter. At near-infrared wavelengths, scattering is minimal and the true photosphere is seen. In the mid-infrared, thermal emission from the atmosphere again increases the apparent size. Studies from 2009 supported the presence of dust and molecular shells around the star, measuring diameters between 42.57 and 44.28 milliarc seconds, with small margins of error. Later observations in 2011 and 2014 confirmed these numbers. At a Hipparcos distance of 152 parsecs, the near-infrared photosphere spans about 3.4 AU, or 730 solar radii. Between 1993 and 2009, Betelgeuse's apparent radius shrank by about 15%, measured at one wavelength over 15 years. The angular diameter decreased from 56.0 milliarc seconds in 1993 to 47.0 milliarc seconds in 2008, equivalent to a contraction of almost 0.9 AU. This change is thought to reflect variations in the outer layers rather than the star's core. Current models adopt a photospheric diameter of around 43 milliarc seconds, with additional shells extending to 50 to 60 milliarc seconds. At a distance of 197 parsecs, this gives a stellar diameter of roughly 887 solar radii, plus or minus 203 solar radii. Betelgeuse was once considered to have the largest angular diameter of any star in the sky after the Sun. In 1997, however, astronomers measured the nearby star R Doradus at 57 milliarc seconds, surpassing Betelgeuse in apparent size. Because R Doradus is much closer, about 200 light-years away, its actual diameter is only about a third of Betelgeuse's true size. Betelgeuse lies far enough from the plane of the ecliptic that the major planets cannot pass in front of it, a phenomenon known as an occultation. However, smaller objects such as asteroids, which are far more numerous and have wider-ranging orbits, frequently cross in front of the star. For example, a partial occultation occurred on the 2nd of January 2012, when the asteroid 147,857 2005 UWW 381, which has a faint brightness of 19th magnitude, passed in front of Betelgeuse. The event was only partial because the star's apparent size in the sky is larger than that of the asteroid, so the drop in brightness was very small, about 1/100th of a magnitude. Another predicted occultation involved the 14th magnitude asteroid 319 Leona, expected on the 12th of December 2023 at 1:12 Coordinated Universal Time. Initially, it was unclear whether the star would be completely covered, and early calculations suggested that the occultation might last only around 12 seconds, visible along a narrow path on Earth whose exact width and location were uncertain due to incomplete knowledge of the asteroid's size and path. Later, as astronomers collected more precise data, the prediction was refined. The totality, sometimes referred to as a ring of fire, was estimated to last approximately 5 seconds, with a path about 60 kilometers wide stretching from Tajikistan through Armenia, Turkey, Greece, Italy, Spain, across the Atlantic Ocean, through Miami, Florida and the Florida Keys, all the way to parts of Mexico. This fortunate event also allowed astronomers to study the asteroid itself in detail. More than 80 amateur astronomers across Europe were coordinated for the event by astrophysicist Miguel Montages and his colleagues at the Paris Observatory. Betelgeuse is an enormous, bright but relatively cool star, classified as an M1 to 2 Ia-Ab red supergiant. The M indicates that it is a red star in the M spectral class, meaning it has a relatively low surface temperature. The Ia-Ab luminosity class shows that it is an intermediate luminosity supergiant, falling somewhere between a normal supergiant and a very luminous supergiant. Since the year 1943, astronomers have used Betelgeuse's spectrum as a stable reference point for classifying other stars. Determining Betelgeuse's luminosity is challenging because its surface temperature, diameter, and distance are not precisely known. Research from 2012 estimates its brightness at roughly 126,000 times the luminosity of our Sun, assuming it is about 200 parsecs away. Studies from 2001 onward suggest surface temperatures ranging from 3,250 to 3,690 kelvins, though other values have been reported. Much of this variation appears to be real, caused by pulsations in the star's atmosphere. Betelgeuse rotates slowly, with the latest measured rotational speed being 5.45 km per second, far slower than Antares, which rotates at 20 km per second. Its rotation period, depending on its size and orientation toward Earth, is estimated at 36 years, with an axis tilted roughly 60 degrees relative to our line of sight. In 2004, computer simulations suggested that even if Betelgeuse were not rotating, it might still show significant magnetic activity in its vast outer layers. Even moderate magnetic fields could influence the star's dust, winds, and the way it loses mass. Observations in 2010 using the Bernard-Liot telescope at Pic du Midi Observatory confirmed the presence of a weak magnetic field at the star's surface, indicating that the enormous convective motions inside a supergiant can trigger a small-scale magnetic dynamo. Modern theoretical models estimate Betelgeuse's mass between 9.5 and 21 times that of the Sun, though older studies suggested a wider range of 5 to 30 solar masses. Calculations indicate that Betelgeuse likely formed with a mass between 15 and 20 solar masses, based on an initial brightness between 90,000 and 150,000 times that of the Sun. A method developed in 2011, using observations from narrow H-band interferometry and measuring the star's photosphere at roughly 4.3 astronomical units, or 955 plus or minus 217 solar radii, suggested a current mass of 11.6 solar masses, with possible upper and lower limits of 16.6 and 7.7 solar masses. Other probabilistic analyses place its current mass at 16.5 to 19 solar masses, with an initial mass of 18 to 21 solar masses. Betelgeuse's mass can also be inferred from its position on the color magnitude diagram. Historical records suggest that over the last few thousand years, Betelgeuse's color may have shifted from yellow or possibly orange to red. This, combined with its placement on the diagram, suggests a mass of around 14 solar masses, an age of 14 million years, and a distance of roughly 125 to 150 parsecs, equivalent to about 400 to 500 light-years. The star's movement through space is complex. Stars in the M supergiant class with initial masses of 20 solar masses typically live for about 10 million years. Extrapolating Betelgeuse's motion backward places it roughly 290 parsecs above the galactic plane, a location with no known star formation, making such a position unlikely. Its projected path also does not intersect with the 25 Orion subassociation, or the much younger Orion Nebula cluster. Observations from the Very Long Baseline Array suggest that Betelgeuse is between 389 and 414 parsecs from the Orion Nebula cluster. This indicates that Betelgeuse's motion has likely changed over time, possibly as a result of a nearby stellar explosion. Images from the Herschel Space Observatory in January 2013 revealed that the star's powerful winds are colliding with the surrounding interstellar medium. The most plausible explanation for Betelgeuse's origin is that it is a runaway star from the Orion OB1 association. It was probably born as part of a massive multiple star system within Ori OB1A about 10 to 12 million years ago, but has evolved rapidly because of its large mass. In 2015, H. Bowie and J. Alves proposed that Betelgeuse might instead belong to the newly discovered Tarian-OB association. In the final stages of a massive star's life, stars like Betelgeuse lose enormous amounts of mass, sometimes as much as one solar mass every 10,000 years. This constant shedding of material creates a highly complex and ever-changing environment around the star. In a paper published in 2009, scientists described stellar mass loss as the key to understanding the evolution of the universe from its earliest moments to the present day, as well as the formation of planets and even life itself. Despite its importance, the exact process behind this mass loss is still not fully understood. The late astronomer Martin Schwarzschild first suggested that enormous convection cells, giant bubbles of rising and falling gas within the star, might be responsible for the loss of mass in supergiants like Betelgeuse. Recent research supports this idea, but there remain many uncertainties about the structure of these convection cells, the mechanisms driving mass loss, how dust forms in the star's extended atmosphere, and the precise conditions that lead to its dramatic end as a Type II supernova. In 2001, astronomer Graham Harper estimated Betelgeuse's stellar wind at about 0.03 solar masses every 10,000 years. However, later studies after 2009 found that the star loses mass in episodes rather than steadily, making any exact figure uncertain. Current observations suggest that a star like Betelgeuse may spend part of its life as a red supergiant, then evolve back across the Hertzsprung-Russell diagram, briefly become a yellow supergiant, and ultimately explode either as a blue supergiant or a Wolf-Rayet star. Astronomers are gradually unravelling this mystery. They observed a massive plume of gas stretching at least 6 times the star's radius, which indicates that Betelgeuse does not shed material evenly in all directions. This plume shows that the star's normally spherical photosphere, especially visible in infrared light, is disrupted near the star. Asymmetries on the stellar disk had been noted before at different wavelengths, but with the improved resolution of the NACO adaptive optics system on the Very Large Telescope, these irregularities became much clearer. The 2 likely causes of such uneven mass loss are either the presence of giant convection cells or mass loss concentrated at the poles, possibly caused by the star's rotation. Using ESO's AMBER instrument, astronomers observed gas in the extended atmosphere moving vigorously up and down, forming bubbles as large as the star itself. This led them to conclude that such violent stellar motion is behind the massive plumes detected by Covella. Betelgeuse's atmosphere is far more complex than just its visible surface. Scientists have now identified 6 additional components: a molecular layer called the Heliosphere, a gaseous envelope, a chromosphere, a dust environment, and 2 outer shells composed of carbon monoxide known as S1 and S2. Some of these layers are irregular, while others overlap. At roughly 0.45 stellar radii, or about 2 to 3 astronomical units, above the photosphere, the Molsphere contains water vapor and carbon monoxide, with an effective temperature of around 1,500 Kelvin, plus or minus 500. Water vapor in Betelgeuse's spectrum was first detected in the 1960s using the 2 stratoscope missions, though it was largely ignored for decades. The Molsphere may also include silicon monoxide and aluminum oxide, molecules that can help form dust. Further out lies the cooler asymmetric gaseous envelope, extending approximately 10 to 40 astronomical units from the star. This region is rich in oxygen, and especially nitrogen relative to carbon, likely due to material from Betelgeuse's interior processed through nuclear reactions. Radio telescope images from 1998 confirmed that the star has a highly complex atmosphere, with temperatures of roughly 3,450 Kelvin, plus or minus 850. Although this is similar to the star's surface temperature, it is much cooler than surrounding gas in the same region. These observations revealed that this lower temperature gas is the most abundant part of Betelgeuse's atmosphere, and that it gradually cools as it extends outward. Jeremy Lim, who led the research, explained that instead of a uniform expansion of hot gas, giant convection cells propel material from the star's surface into the atmosphere. This is likely the same region where Covella discovered the bright plume in 2009, which contains carbon and nitrogen and stretches at least 6 times the photospheric radius in the southwest direction. The chromosphere, another atmospheric layer, was directly imaged by the Faint Object Camera on the Hubble Space Telescope in ultraviolet light. These images revealed a bright area in the southwest quadrant of the star's disk. In 1996, the chromosphere's average radius was about 2.2 times the visible disk, roughly 10 astronomical units, with a temperature not exceeding 5,500 Kelvin. By 2004, high-precision observations with Hubble's STIS instrument suggested the presence of warm chromospheric plasma at least 1 arcsecond away from the star. At a distance of 197 parsecs, this plasma could extend up to 200 astronomical units. Observations confirmed that the warm chromosphere coexists with the cooler gas in the envelope and with the surrounding dust shells. The first suggestion that Betelgeuse is surrounded by a dust shell came in 1977, when astronomers noted that mature stars often emit extra radiation from surrounding dust. Interferometry revealed that most of this excess radiation comes from beyond 12 stellar radii, comparable to the Kuiper belt at roughly 50 to 60 astronomical units. Subsequent studies at different wavelengths yielded varying results, with estimates in the 1990s placing the inner dust shell between 0.5 and 1 arcsecond, or about 100 to 200 astronomical units. The dust envelope is not static. In 1994, Betelgeuse was reported to undergo sporadic, decades-long episodes of dust production, followed by quiet periods. By 1997, significant changes in the dust shell's shape were observed within a single year, suggesting that it is unevenly illuminated by the star, influenced by hotspots on the photosphere. Earlier reports in 1980 of a giant asymmetric dust shell extending 1 parsec, or about 206,265 astronomical units, have not been confirmed, although other studies that same year noted 3 dust shells extending 4 light-years from one side of the star, suggesting ongoing shedding of outer layers. The exact sizes of the 2 outer carbon monoxide shells remain uncertain. Preliminary estimates indicate that the inner shell stretches from roughly 1.5 to 4 arcseconds, while the outer shell reaches about 7 arcseconds. Assuming a stellar radius similar to the orbit of Jupiter, around 5.5 astronomical units, the inner shell would extend approximately 50 to 150 stellar radii, or about 300 to 800 astronomical units, and the outer shell could reach roughly 250 stellar radii, or about 1,400 astronomical units. By comparison, the Sun's heliopause is estimated at 100 astronomical units, so Betelgeuse's outer shell would be nearly 14 times the size of the solar system. Betelgeuse is moving through the space between stars, known as the interstellar medium, at a speed of 30 kilometers per second, which is roughly equivalent to 6.3 astronomical units per year. As it travels, it produces a bow shock, a sort of cosmic wave in front of it. Interestingly, this shock is not caused directly by the star itself, but by its incredibly strong stellar wind. This wind blows out enormous amounts of gas at a speed of 17 kilometers per second, which then heats the material around Betelgeuse, making it glow brightly in infrared light. Despite Betelgeuse being such a prominent and luminous star, it was not until the year 1997 that astronomers were able to capture an image of this bow shock for the first time. The bow shock appears comet-like in shape and is estimated to stretch at least 1 parsec across, based on Betelgeuse's distance of 643 light-years from Earth. Computer simulations of the bow shock created in 2012 show that it is actually very young, less than 30,000 years old. This has led scientists to consider 2 main possibilities. One is that Betelgeuse may have recently moved into a part of the interstellar medium with different properties, which changed how the bow shock formed. The other is that the star itself may have gone through a major transformation, which altered the behavior of its stellar wind. A study from 2012 suggested that this could be linked to Betelgeuse transitioning from a blue supergiant to a red supergiant. Evidence indicates that stars like Betelgeuse, during their late evolutionary stages, can shift quickly from red to blue or vice versa on the Hertzsprung-Russell diagram, and these shifts are accompanied by rapid changes in both their stellar winds and the bow shocks they create. If future studies confirm this idea, it is possible that Betelgeuse, as a red supergiant, may have travelled nearly 200,000 astronomical units through space, shedding up to 3 solar masses of material along its path. This means the star has not only been moving swiftly through the cosmos, but it has also been actively shaping its surroundings, leaving behind a trail of gas and dust as it journeys through the galaxy. Betelgeuse is a red supergiant star, a massive star that has gone through dramatic changes during its life. It began its existence as a hot, very bright O-type main sequence star, known for burning hydrogen at its core at incredible rates. Once the hydrogen in its core ran out, Betelgeuse transformed into a blue supergiant for a period of time before eventually cooling and expanding into the enormous red supergiant we observe today. In the distant future, the core of Betelgeuse will collapse, triggering a spectacular supernova explosion, leaving behind a dense remnant, such as a neutron star or a black hole. The exact nature of this final fate depends on the star's original mass and other properties it had when it first formed. Estimating Betelgeuse's initial mass is not straightforward. Astronomers use stellar evolution models, which simulate the life cycles of stars, to see which combinations of mass, rotation, and composition best match what we observe now. Because both the models and the current measurements have uncertainties, there is still some debate about the star's earliest properties. However, most estimates suggest that Betelgeuse was born with a mass somewhere between 10 and 25 times that of our Sun, with modern models favouring a range of 15 to 20 solar masses. Its original chemical makeup likely included about 70% hydrogen, 28% helium, and roughly 2.4% heavier elements, making it slightly richer in metals than the Sun, but otherwise similar. The star's initial spin rate is less certain, but models that assume slow to moderate rotation seem to best match Betelgeuse's current characteristics. Back in its main sequence days, Betelgeuse would have been a luminous, extremely hot star with a spectral type around 09V. The time it took Betelgeuse to reach the red supergiant stage depends on its mass and how fast it rotated. A star with 15 solar masses could take between 11.5 million and 15 million years to become a red supergiant, with faster spinning stars taking the longer time. A 20 solar mass star spinning quickly might take around 9.3 million years, while a slow spinning 20 solar mass star could reach this stage in about 8.1 million years. Based on these models, Betelgeuse is currently estimated to be around 8 to 8.5 million years old if it started with 20 solar masses and no significant rotation. Determining how long Betelgeuse has already been a red supergiant involves examining its surrounding material and the elements visible at its surface. Estimates suggest it has been in this phase anywhere from 10,000 to a maximum of 140,000 years. Betelgeuse appears to lose mass in bursts and moves rapidly through space as a runaway star, which makes calculating the total mass loss challenging. Its surface shows signs of nuclear fusion processing. Nitrogen levels are elevated, carbon is relatively low, and the isotope ratio of carbon-13 to carbon-12 is high. These features indicate the star has undergone the first dredge-up, a mixing process that occurs early in the red supergiant phase. This means Betelgeuse has been a red supergiant for at least several thousand years, with the best estimate being around 40,000 years, having left the main sequence roughly 1 million years ago. From these evolutionary models, Betelgeuse's current mass is estimated by subtracting the mass it has likely lost from its initial mass. So far, it may have lost no more than about 1 solar mass, suggesting it now has a mass of approximately 19.4 to 19.7 solar masses. This is notably higher than other estimates derived from pulsations or limb-darkening models. Stars that begin with more than around 10 solar masses are expected to end their lives in a core collapse supernova. For stars up to roughly 15 solar masses, this usually results in a Type 2p supernova directly from the red supergiant stage. Heavier stars may lose mass quickly enough to evolve to hotter temperatures before collapsing, particularly if they rotate rapidly or have exceptionally high mass loss rates. These stars can produce different supernova types, Type 2L or Type 2b from yellow or blue supergiants, or Type 1bc from Wolf-Rayet stars. Models suggest that a rotating 20 solar mass star could produce a peculiar Type 2 supernova, similar to the famous SN 1987A, originating from a blue supergiant, while a non-rotating 20 solar mass star would produce a more typical Type 2p supernova from a red supergiant. The remaining time before Betelgeuse explodes depends on its initial properties and how long it has already been a red supergiant. The total lifespan from the start of the red supergiant phase until core collapse could range from about 300,000 years for a rotating 25 solar mass star, 550,000 years for a rotating 20 solar mass star, and up to 1 million years for a non-rotating 15 solar mass star. Considering that Betelgeuse has already been a red supergiant for around 40,000 years, its remaining life is likely under 100,000 years in a non-rotating 20 solar mass scenario, though it could be longer if it rotates or is less massive. Betelgeuse is thought to have formed in the Orion-OB1 association, a stellar nursery that has already produced multiple supernovae. Runaway stars, like Betelgeuse, may be ejected from clusters due to past supernova explosions. Strong evidence shows that stars such as Columbae, AE Aurigae, and 53 Arietis were all expelled from the Orion-OB1 association during supernovae events 2.2, 2.7, and 4.9 million years ago, respectively. When Betelgeuse finally explodes as a Type 2P supernova, it would release an immense amount of energy. The event would emit around 2 × 10 to the 46 joules of neutrinos and produce a kinetic energy of about 2 × 10 to the 44 joules. Seen from Earth, the explosion could reach a peak apparent brightness somewhere between -8 and -12 magnitude, making it easily visible during the day and potentially rivaling the brightness of a large fraction of the full moon, though likely not surpassing it. The supernova would stay roughly at this brightness for about 2 to 3 months before fading rapidly. Most of the visible light would come from the radioactive decay of cobalt-56, with the cooling hydrogen ejected by the explosion allowing its light to shine for so long. Because of misunderstandings stemming from a scientific paper published in 2009, which reported that Betelgeuse appeared to have shrunk by about 15%, mostly in its outer atmosphere, the star has often been the focus of alarming stories and rumours. These reports frequently suggested that Betelgeuse might explode within a single year, and sometimes exaggerated the potential consequences of such an explosion. The timing and spread of these rumours have been linked to broader misconceptions about astronomy, particularly those tied to doomsday predictions related to the supposed Mayan calendar apocalypse. In reality, Betelgeuse is very unlikely to produce a gamma-ray burst, and it is far enough away that its X-rays, ultraviolet radiation, or ejected material would not have any significant impact on Earth. When Betelgeuse dimmed noticeably in December 2019, both scientific and mainstream media once again reported speculation that the star could be on the verge of exploding as a supernova. This happened despite research showing that a supernova is not expected for perhaps 100,000 years. Some publications, such as Astronomy Magazine, National Geographic, and the Smithsonian, noted the star's unusual dimming, with its brightness reaching a magnitude as faint as +1.3, presenting it as a remarkable and interesting event. Some media outlets, like the Washington Post, ABC News in Australia, and Popular Science, clarified that while a supernova is theoretically possible, it is extremely unlikely. Other outlets, however, presented the explosion as a near-certain event, exaggerating the risk. For instance, CNN ran the headline, "A giant red star is acting weird and scientists think it may be about to explode," while the New York Post declared that Betelgeuse was due for explosive supernova. Scientists like Phil Plett, writing on his Bad Astronomy blog, emphasized that while Betelgeuse's recent behavior is unusual, it is not unprecedented, and the star is unlikely to explode for a long time. Dennis Overby of the New York Times agreed that an explosion is not imminent, but added that astronomers are enjoying the process of studying it. Eventually, when Betelgeuse does explode as a supernova, it will leave behind a small, dense remnant, either a neutron star or a black hole. Current evidence suggests that Betelgeuse does not have a core massive enough to form a black hole, so the remnant is most likely to be a neutron star with a mass of approximately 1.5 times the mass of the Sun. Betelgeuse has generally been thought to be a single star. However, in studies published in 1985 and 1986, a team led by Margarita Karowska analysed polarization data collected between 1968 and 1983 and found indications of 2 companion stars. The closer companion appeared to orbit the main star every 2.1 years, and, based on speckle interferometry, was estimated to be about 0.06 arc-seconds, or 9 astronomical units, from Betelgeuse. This orbit might place it within the star's outer chromosphere. The more distant companion was found at 0.51 arc-seconds, or 77 astronomical units, with a slightly different position angle. V838 Monocerotis, also known as Nova Monocerotis 2002, is an extraordinary and dramatic star system located in the constellation Monoceros, the Unicorn, roughly 19,000 light-years away from our Sun, or about 6,000 parsecs. Before the year 2002, this star had gone largely unnoticed, blending quietly among countless others. However, in early 2002, astronomers observed a sudden and massive outburst, turning this previously ordinary star into one of the largest stars ever recorded, at least for a short period following the eruption. Initially, astronomers thought it was a typical nova, a common type of stellar explosion, but further study revealed something much more unusual: V8. 38 Monocerotis represented the first example of a new class of eruptive stars now called luminous red novae. The exact cause of this violent outburst is still not fully understood, though it is widely believed that it involved the merger of two stars in a triple star system. The eruption occurred in one of the two B3-type main sequence stars that orbit each other closely within the system. During the outburst, the erupting star expanded dramatically and temporarily enveloped its companion, appearing as an unusually cool and enormous supergiant. By the year 2009, the star had heated up since 2005 to a surface temperature of 3,270 Kelvin, shone with a brightness about 15,000 times that of the Sun, and had shrunk to a radius approximately 380 times larger than the Sun. Meanwhile, the material ejected during the eruption continued to spread outward into space. The event was first noticed on January 6, 2002, when a previously unknown star suddenly brightened in Monoceros. As a newly discovered variable star, it was officially designated V838 Monocerotis, the 838th variable star catalogued in that constellation. Because the initial brightness increase resembled a classical nova, an eruption that happens when a white dwarf star gathers enough hydrogen from a nearby companion, it was also called Nova Monocerotis 2002. The star reached its peak brightness at a visual magnitude of 6.75 on February 6, 2002, before beginning to fade rapidly, as would be expected for a typical nova. Surprisingly, in early March, the star brightened again, especially in the infrared part of the spectrum, followed by yet another infrared brightening in early April. By 2003, V8, 38 Monocerotis had returned to almost its pre-eruption brightness, at magnitude 15.6, but now it appeared as a red supergiant rather than the blue main sequence star it had been before. The shape of its light curve, the way its brightness changed over time, was unlike anything astronomers had ever observed. At the height of its eruption, V838 Monocerotis became astonishingly luminous, shining roughly 1 million times brighter than the Sun, with an absolute magnitude of -9.8. This made it one of the brightest stars in the Milky Way galaxy at that moment. The intense brightening was caused by a rapid swelling of its outer layers. Observations with the Palomar testbed interferometer measured the star's radius at roughly 1,570 times the Sun's radius, comparable to the distance from the Sun to Jupiter, confirming earlier indirect calculations. With the currently accepted distance of 6,100 parsecs, the angular diameter measured in late 2004 corresponded to a radius of approximately 1,200 solar radii. By 2014, the star had shrunk to about 750 solar radii, still around 70 times larger than the star Antares. The expansion and contraction occurred astonishingly fast, in only a few months, causing the star to cool dramatically due to the laws of thermodynamics. Its deep red colour became extreme, and for a time its spectrum resembled that of L-type brown dwarfs. If this interpretation is correct, V838 Monocerotis may have been the first known L-type supergiant. Since then, it has gradually shrunk and heated up again, now classified as an M-type supergiant. However, more recent distance measurements suggest that the earlier estimates of its size were about 25% too high. V8. 3. 8. Monocerotis is not entirely unique. Similar outbursts have been observed before. In 1988, a red star in the Andromeda Galaxy, designated M31RV, erupted to an absolute bolometric magnitude of -9.95, equivalent to a luminosity of approximately 750,000 times that of the Sun, before fading out of detectability. Another similar eruption, V4332 Sagittarii, occurred in the Milky Way in 1994. Early measurements of V838 Monocerotis' distance were incorrect. Based on a mistaken interpretation of the light echo, the reflection of the eruption off surrounding dust, the star was initially thought to be between 1,900 and 2,900 light-years away. This led astronomers to believe it was a relatively small, underluminous F-type dwarf, creating a puzzling mystery. Later, more accurate measurements placed the star at a distance of about 20,000 light-years, indicating that it was much more massive and luminous than the Sun. Current estimates suggest that V838 Monocerotis has a mass between 5 and 10 times that of the Sun. The system likely consisted of either a B1.5 main sequence star with a B3 companion, or an A0.5 main sequence star with a B4 companion. In the second case, the erupting star would have had a luminosity of around 550 times that of the Sun, roughly 43% as bright as its companion. In the first scenario, it would have been more luminous, about 1.9 times the brightness of its companion. Originally, the star may have had a radius around 5 times that of the Sun, and a temperature typical of a B-type star, somewhere above 10,000 Kelvin, but below 30,000 Kelvin. Some researchers, such as Minari and colleagues in 2005, proposed that the progenitor was a very massive supergiant of roughly 65 solar masses, although this idea is debated. All agree that the system is relatively young, possibly only about 4 million years old. The spectrum of V838 Monocerotis reveals the presence of a hot blue B-type main sequence companion, which may not have been very different from the erupting star before the outburst. It is also possible that the erupting star was slightly less massive than this companion, and had just recently entered the main sequence phase. Using measurements of the companion, Minari and colleagues estimated an even greater distance for the system, around 36,000 light-years, or 10,000 parsecs. When certain stars suddenly brighten, such as in novae or supernovae, they can create a remarkable phenomenon known as a light echo. In simple terms, the light that travels straight from the star reaches observers first. However, if clouds of interstellar dust or gas surround the star, some of the light bounces off these clouds before reaching us. Because this reflected light travels along a path, it arrives slightly later, creating the illusion of expanding rings of light surrounding the brightened star. These rings may appear to move faster than the speed of light, but this is only a visual effect. No physical object is actually breaking the cosmic speed limit. In the case of V838 Monocerotis, the light echo produced was unlike anything astronomers had seen before. It is exceptionally well documented in photographs taken by the Hubble Space Telescope. At first glance, the images seem to show a perfectly spherical shell of material expanding outward from the star, but the reality is more subtle. The glowing shapes are actually formed by the illumination of a three-dimensional ellipsoid, with the original star at one focus and the observer, here on Earth, at the other. This means that the structures seen in the photos are concave toward the viewer, creating a striking but deceptive visual effect. By March of 2003, the light echo had grown so large that its angular size in the sky was about twice that of Jupiter, and it continued to expand. For context, Jupiter's angular diameter, as seen from Earth, changes between 30 and 51 arcseconds depending on its position. Astronomers are still uncertain whether the nebulous clouds surrounding V838 Monocerotis are directly associated with the star itself. If they are, it is possible that they were created by earlier eruptions from the star, which would challenge several models that assume a single catastrophic outburst. Strong evidence, however, suggests that V838 Monocerotis is a very young star system, still embedded in the original nebula from which it formed. During the eruption, the star initially emitted light at shorter wavelengths, meaning the light was bluer. This effect is visible in the light echo, where the outer edges of the echo appear bluish in Hubble images. Events like this, classified as luminous red novae, are now generally believed to result from the merger of two stars. In the case of V838 Monocerotis, the eruption likely occurred when two stars combined, either two main sequence stars or an 8 solar mass main sequence star merging with a smaller, approximately 0.3 solar mass, pre-main sequence star. This merger model also explains why astronomers observed multiple peaks in the star's light curve during the outburst. Studies of similar stars, such as V1309 Scuti, support the idea that stellar mergers are the most probable cause. Other theories about the eruption of V838 Monocerotis have also been suggested. One possibility is that the outburst could be a type of nova, but this is considered highly unlikely because the system contains a B-type star, which is young and massive. Such stars would not have had enough time for a white dwarf companion to cool and accumulate the material needed to trigger a nova eruption. Another theory proposes that V838 Monocerotis could be a post-asymptotic giant branch star, nearing a supernova. In this scenario, the surrounding nebulosity illuminated by the light echo could be shells of dust ejected by previous eruptions. The sudden brightening could be a so-called helium flash, in which the core of a dying, low-mass star suddenly ignites helium fusion without destroying the star, a phenomenon previously observed in Sakurai's object. However, multiple lines of evidence point to the dust being interstellar rather than directly surrounding the star, and to the star itself being young rather than old and dying. Some scientists have suggested that V838 Monocerotis might be an extremely massive supergiant. In this case, the outburst could still be a helium flash. Very massive stars can survive several helium flashes, but they lose a significant fraction of their mass, around half, while still on the main sequence, eventually becoming extremely hot Wolf-Rayet stars. This scenario could also explain the apparent dust shells observed around the star. Interestingly, V8. 38 Monocerotis is located toward the outer edge of the Milky Way, away from the main disk, where star formation is less active. This raises questions about how such a massive star could form there, though there are known young clusters, such as Ruprecht 44 and the 4-million-year-old NGC 1893, located approximately 7 and 6 kiloparsecs away, respectively. Yet another possibility is that V838 Monocerotis may have engulfed one or more of its giant planets. If a planet fell into the star's atmosphere, the drag from the stellar gas would slow the planet, and as it plunged deeper, friction would heat the star's envelope. This could trigger deuterium fusion and cause the star to rapidly expand. Subsequent peaks in brightness might then occur if additional planets entered the inflated envelope. Calculations suggest that about 0.4 planetary engulfment events occur every year for Sun-like stars in the Milky Way, while for massive stars like V838 Monocerotis, the rate could range from approximately 0.5 to 2.5 events per year. Canis Majoris is an extraordinary and extreme star located in the slightly southern constellation of Canis Major, the Great Dog. It is classified as an oxygen-rich red hypergiant, or red supergiant, and it is also a pulsating variable star, meaning its brightness changes over time. This remarkable star lies approximately 1,200 parsecs, or about 3,900 light-years, away from the solar system. Among the largest stars known to astronomers, Canis Majoris is also one of the most massive, luminous, and impressive red supergiants in our Milky Way galaxy. There is no evidence that VYCMA belongs to a multiple star system, making it a solitary giant. Its strong emission of infrared light makes it one of the brightest objects in the nearby Orion arm of the Milky Way when observed at wavelengths between 5 and 20 microns. This intense infrared brightness is caused by a shell of dust or a heated disk surrounding the star. Canis Majoris has a mass estimated to be about 17 times that of the Sun, with a margin of error of plus or minus 8 solar masses. Surrounding it is a complex and uneven circumstellar envelope, formed from the enormous amounts of material the star has shed into space. This star is a powerful source of molecular masers, natural amplifiers of microwave radiation, and was among the first stars observed to produce radiomasers. Canis Majoris is embedded within a large molecular cloud known as SH2310, a nearby region where new stars are actively forming. This cloud spans an impressive diameter of 480 arc-minutes, which corresponds to roughly 681 light-years. Due to its immense size and fiery brilliance, astronomers have sometimes described VYCMA as Betelgeuse on steroids. The radius of Canis Majoris is estimated to be about 1,420 times larger than the radius of the Sun. This enormous size is near the theoretical maximum for a star of this type, known as the Hayashi limit. In terms of volume, this radius corresponds to almost 3 billion times the volume of our Sun. To give some perspective, if a spacecraft could travel at the speed of light, it would take approximately 6 hours to travel once around the surface of Canis Majoris, compared to just 14.5 seconds to circle the Sun. If VYCMA replaced the Sun in our solar system, its surface would extend beyond the orbit of Jupiter, swallowing the inner planets entirely. The first recorded observation of Canis Majoris was made by the French astronomer Jérôme Lalande in 1801. He listed it in his star catalogue as a star of 7th magnitude. Later observations show that its apparent brightness as seen from Earth has decreased slightly since around 1850, possibly due to changes in the star's emissions or the movement of denser regions in the surrounding dust blocking some of its light. Since 1847, astronomers have consistently described the star as having a deep crimson colour. During the 19th century, observers thought they had detected at least 6 separate components, suggesting VYCMA might be part of a multiple star system. Modern high-resolution imaging, particularly observations from 1957 and 1998, revealed that these components were actually bright regions in the surrounding nebula, not companion stars. Canis Majoris is also a strong emitter of specific molecular masses, including hydroxyl, OH, at 1612 MHz, water, H2O, at 22,235.08 MHz, and silicon monoxide, SiO, at 43,122 MHz, which is characteristic of OH-IR stars. Scientists have also detected a variety of molecules in its envelope, including hydrogen cyanide, HCN, sodium chloride, NaCl, phosphorus nitride, PN, methylidine, CH, carbon monoxide, CO, methanol, CH3OH, titanium monoxide, TiO, and titanium dioxide, TiO2. The star's variability was first formally noted in 1931, when it was classified in German as a long-period variable star with a photographic magnitude ranging from 9.5 to 11.5. In 1939, it received its official variable star designation, VY Majoris, as the 43rd variable star recorded in the constellation Canis Major. By combining observations from various telescopes, including the Keck Observatory in Hawaii, astronomers were able to create a 3-dimensional reconstruction of the star's circumstellar envelope. This revealed that VYCMA loses mass in a far more complicated manner than expected for any red supergiant or hypergiant. The bow-like structures and dense knots in the surrounding material were found to form at different times, and the jets of expelled material are oriented randomly. This suggests that these eruptions may result from localized explosions in the star's photosphere, similar in nature, but vastly larger, to the coronal mass ejections of our Sun. Spectroscopic measurements confirm that these jets move away from the star at different speeds, indicating multiple separate events. Scientists estimate that many of these asymmetric mass loss events and the ejection of the outermost layers have occurred within the last 500 to 1,000 years, while certain knots of material near the star may have been expelled less than 100 years ago. This dramatic and ongoing shedding of mass is driven by powerful convection in the star's tenuous outer layers, coupled with its magnetic fields, producing phenomena that dwarf anything seen in smaller stars. In the year 1976, astronomers Larder and Reed published detailed observations of a bright-rimmed molecular cloud known as Scuti-310. This cloud lies about 15 arc-seconds to the east of a massive star in the same region. At the edge of the cloud, next to the bright rim, they noticed an abrupt drop in the carbon monoxide emission and, simultaneously, a rise in the emission from the carbon monoxide isotope 12. This suggested that molecular material at the edge of the cloud might be getting destroyed, while the increased emission indicated that the gas there was being heated more than in other areas. The researchers assumed that the cloud was roughly at the same distance as nearby stars, which are part of the open star cluster NGC 2362 and are responsible for ionizing the rim of the cloud. NGC 2362 is thought to lie at a distance somewhere around 1.5 kiloparsecs, plus or minus half a kiloparsec, which translates to roughly 4,890 light-years, with a possible error of about 1,630 light-years, based on the cluster's color magnitude diagram. One of the stars appears projected right at the tip of the cloud's bright rim, strongly hinting at a physical connection. Moreover, the measured velocities of H2-310 closely match those of the star, supporting the idea that the star, the cloud, and the cluster are all physically associated according to standard astrophysical models. H2-310 is not only home to this star and NGC 2362, but also hosts several dark nebulae, including LDN 1660, LDN 1664, and LDN 1667. The cloud also contains several bright stars such as Tau Canis Majoris, the brightest member of NGC 2362, along with UW Canis Majoris and HD 58011. These stars, together with VY Canis Majoris, are thought to contribute significantly to the ionization of gases within H2-310. The cloud itself sits on the outer edge of the Orion arm of our Milky Way galaxy. Later studies by Melnick and colleagues suggested a somewhat smaller preferred distance for the cloud, centered around 1.2 kiloparsecs, or about 3,900 light-years. Astronomers can calculate stellar distances by measuring how a star's position appears to shift against very distant background objects as Earth orbits the Sun, a method known as parallax. However, Canis Majoris is so distant that its parallax is very small, making traditional visual measurements unreliable. For example, the Hipparcos catalogue of 1997 recorded a parallax of 1.78 milliseconds, with an error of plus or minus 3.54 milliseconds, implying a notional distance of 562 parsecs, or 1,832 light-years, an estimate too uncertain for a hypergiant star surrounded by an extended circumstellar envelope. More accurate measurements come from observing masers using long baseline interferometry. In 2008, observations of water masers using the VIRA interferometry array from the National Astronomical Observatory of Japan measured a parallax of 0.88 milliseconds, with an error of plus or minus 0.08 milliseconds. This corresponds to a distance of roughly 1.14 kiloparsecs, or 3,720 light-years, with an uncertainty range from about 3,600 to 4,080 light-years. Then, in 2012, observations of silicon monoxide masers using very long baseline interferometry with the Very Long Baseline Array independently found a parallax of 0.83 milliseconds, plus or minus 0.08, corresponding to a distance of 1.2 kiloparsecs, or about 3,910 light-years. These results suggest that the Cloud 2-310 is somewhat closer than previously thought, or that Canis Majoris might lie in front of the cloud. While the Gaia space mission provides highly precise parallaxes for many stars, its second data release reported a value of negative 5.92 milliseconds, with an error of plus or minus 0.83 milliseconds for Canis Majoris, which is not physically meaningful. Canis Majoris itself is a variable star, meaning its brightness changes over time. Its apparent visual magnitude ranges from 9.6 at its dimmest to 6.5 at its brightest, with a pulsation period estimated at 956 days. The General Catalogue of Variable Stars classifies it as a semi-regular variable of subtype SRC, indicating it is a cool supergiant, whereas the American Association of Variable Star Observers Variable Star Index lists it as a type LC slow irregular variable. Other studies have suggested longer pulsation periods of approximately 1,600 and 2,200 days. This star is often considered the prototype for a rare class of heavily mass-losing OH/IR supergiants, which are distinct from the more common asymptotic giant branch OH/IR stars. Its spectrum shows it to be a high luminosity M-class star, though with unusual features. Hydrogen lines in the spectrum display P Cygni profiles typical of luminous blue variables, while the spectrum is dominated by titanium oxide absorption bands, suggesting a classification around M5. The H-alpha line is not visible, but there are unusual emission lines from neutral elements such as sodium and calcium. Depending on which spectral features are emphasized, its luminosity class has been estimated anywhere from bright giant, Roman numeral 2, to bright supergiant, Roman numeral Ia, with a compromise classification of M5 EIBP. Earlier studies sometimes misinterpreted the surrounding nebulosity as companion stars, leading to confusion. Current spectral classification systems struggle to fully describe Canis Majoris. Its spectrum changes over time, and key features vary, making it cooler and redder than a typical M2 star, and generally placing it between M3 and M5. Some studies have even suggested classifications as extreme as M2.5, or as late as M7, which is highly unusual for a supergiant but is seen in other very late type OH/IR red supergiants, like Mi Cephei, S Persei and NML Cygni. Its luminosity class is also inconsistent, with some studies suggesting Ia+, indicating a hypergiant or extremely luminous supergiant. Canis Majoris is an enormous and extremely luminous star, recognized as one of the most extreme stars in the Milky Way since the middle of the 20th century, although its exact nature remained uncertain for some time. Its closest analogue is NML Cygni, another notable extreme cool hypergiant in the Cygnus constellation, although NML Cygni has been studied less extensively. By the late 20th century, astronomers agreed that Canis Majoris is a post-main sequence red supergiant, located in the upper right corner of the Hertzsprung-Russell diagram, even though its exact luminosity and temperature remained uncertain. Measurements of its angular diameter varied significantly depending on the wavelength observed. Because most of its fundamental properties depend on distance, early meaningful estimates showed that Canis Majoris is an exceptionally large star, truly one of the giants of our galaxy. The total energy output, or bolometric luminosity, of Canis Majoris can be calculated by studying its spectral energy distribution, or by measuring its bolometric flux. These measurements are obtained through photometry, which records the star's brightness across several visible and infrared bands. Early calculations, which assumed that the star was located at a distance of 1.5 kiloparsecs, approximately 4,900 light-years, suggested that its luminosity ranged between 200,000 and 560,000 times the luminosity of the Sun. These values placed Canis Majoris very close to, or even slightly beyond, the empirical Humphreys-Davidson limit, which is a boundary describing the maximum luminosity for massive stars. One study, using a slightly larger assumed distance of 2.1 kiloparsecs, roughly 6,800 light-years, estimated its luminosity to be nearly 1 million times that of the Sun. In 2006, a luminosity of 430,000 times the Sun's luminosity was calculated by integrating the total radiation from the entire surrounding nebula, since much of the light from the star is absorbed and re-emitted by the surrounding dust. More recent studies have revised the luminosity downwards. Modern estimates, based on distances below 1.2 kiloparsecs, approximately 3,900 light-years, generally place the luminosity below 350,000 times the Sun's luminosity. For example, in 2011, using photometry from 2001, a value of 270,000 plus or minus 40,000 times the Sun's luminosity was calculated. Even more recently, in 2020, a lower luminosity of 178,000 with uncertainties of plus 40,000, 900 and minus 29,900 times, the Sun's luminosity was derived using newer measurements across more wavelengths to better estimate the bolometric flux. Despite these more recent lower estimates, many older calculations can still match current values if adjusted for a distance of 1.2 kiloparsecs. Although Canis Majoris is one of the brightest stars in the Milky Way, most of its visible light is absorbed by the thick envelope of material surrounding it. This means that the star requires a telescope to be seen, but if the envelope were removed, the star would be visible to the naked eye. Most of the star's energy is emitted as infrared radiation, peaking at wavelengths between 5 and 10 micrometers, largely due to reprocessing of the light by the surrounding dust and nebula. Because Canis Majoris does not have a companion star, its mass cannot be measured directly through gravitational interactions. Instead, astronomers estimate its mass by comparing its effective temperature and luminosity with theoretical models of stellar evolution. These comparisons suggest two possible scenarios. If the star rotates, it likely had an initial mass of 25 plus or minus 10 times the Sun's mass, but its current mass is about 15 times the Sun's mass, and it is approximately 8.2 million years old. If the star does not rotate, it may have started with 32 times the Sun's mass, and now has a mass of about 19 times the Sun's mass. Older studies, based on higher luminosity estimates, suggested even larger initial masses for the star, in the range of 40 to 60 times the Sun's mass. Canis Majoris experiences extremely strong stellar winds and loses material at a remarkable rate because of its high luminosity and relatively low surface gravity. Its average mass loss rate is about 5.6 times 10 to the negative 4 times the Sun's mass per year, one of the highest known for any star, even among red supergiants. During the star's most intense mass loss events, the rate likely exceeded 1 times 10 to the negative 3 times the Sun's mass per year. The star has undergone significant mass loss events, probably driven by convection, around 70, 120, 200, and 250 years ago. Material ejected between 1985 and 1995 is responsible for its hydroxyl maester emissions. The effective temperature of Canis Majoris is difficult to determine precisely, but it is well below 4,000 Kelvin, 3,730 degrees Celsius, 6,740 degrees Fahrenheit. Variations in its spectrum indicate that the temperature changes over time. Early estimates based on its spectral type of M5 suggested temperatures below 3000 Kelvin. In 2006, its temperature was calculated to be as high as 3650 plus or minus 25 Kelvin, corresponding to a spectral type of M2.5, though the star is usually classified as M4 to M5. Using this classification and the temperature scale proposed by Emily Levesque, its temperature is estimated to be between 3450 and 3535 Kelvin. Determining the radius of VY Canis Majoris is challenging due to its thick circumstellar envelope. The star is also a pulsating variable, meaning its size changes over time. Early infrared measurements at a wavelength of 2.2 micrometers indicated an angular diameter of 18.7 plus or minus 0.5 milliseconds, corresponding to a radius exceeding 3,000 times the Sun's radius, about 2.1 billion kilometers, 14 astronomical units, about 1.3 billion miles, assuming a distance of 1.5 kiloparsecs. This is far larger than other known red supergiants or hypergiants, although the measurement may overestimate the star's true size due to interference from the surrounding envelope. In contrast, a study in 2006 that ignored the envelope's effects on the observed flux derived a lower luminosity of 60,000 times the Sun's luminosity. This suggested an initial mass of 15 times the Sun's mass and a radius of 600 times the Sun's radius, classifying VY Canis Majoris and NML Sig as normal early-type red supergiants. This study argued that earlier extreme values of 500,000 times the Sun's luminosity and radii, of 2,800 to 3,230 times the Sun's radius, or even up to 4,000 times the Sun's radius, were based on unreasonably low effective temperatures below 3,000 Kelvin. Shortly afterward, in 2006 to 2007, another study estimated the star's radius to be between 1,800 and 2,100 times the Sun's radius, confirming that VY Canis Majoris is a true hypergiant. This calculation used the more reliable temperature range of 3,450 to 3,535 Kelvin and a preferred luminosity of 430,000 times the Sun's luminosity, based on spectral energy distribution integration at the same assumed distance. In the year 2011, astronomers studied VY Canis Majoris at near-infrared wavelengths using a technique called interferometry with the Very Large Telescope. The size of the star that they reported was based on its Rosslund radius, which is the distance from the centre of the star where the optical depth equals 2/3, the same method used to measure the radius of our Sun. From their observations, the team calculated an angular diameter of 11.3 plus or minus 0.3 milliseconds. Given an average distance of 1.17 plus or minus 0.08 kiloparsecs, or approximately 3,820 plus or minus 260 light-years, this corresponded to a stellar radius of about 1,420 plus or minus 120 times the Sun's radius. The high spectral resolution of the observations allowed the astronomers to reduce errors caused by material surrounding the star. Using the measured radius and a flux of 6.3 plus or minus 0.3 times 10 to the minus 13 watts per square centimetre, they derived an effective surface temperature of 3,490 plus or minus 90 Kelvin, corresponding to a spectral type of M4. The authors noted, however, that their measurement of the angular diameter, and therefore the radius of the photosphere, might be slightly too large, which would also imply that the star's true temperature could be a bit higher. In the year 2013, other estimates based on slightly different radius measurements, including the Witkowski and Monnier radius, suggested a mean size of about 2,000 times the Sun's radius. Later that same year, Matsuura and colleagues proposed a competing method for estimating the radius within the star's surrounding envelope, putting it at about 2,069 times the Sun's radius. This calculation was based on a cooler temperature of 2,800 Kelvin and a luminosity of 237,000 times the Sun's luminosity. However, these larger estimates were not consistent with the star's observed spectral type, so the earlier values from 2012 are considered a better match. Most estimates of the star's size refer to the mean boundary of the optical photosphere, while its size in radio wavelengths is thought to be roughly twice as large. With the more accurate 2012 measurements, around 1,420 times the Sun's radius, Canis Majoris remains smaller than some previously reported numbers for other massive red supergiants and hypergiants in our galaxy and beyond, such as Stephenson 2 DFK1. Nevertheless, Canis Majoris is still frequently described as the largest known star, though often with caveats to reflect the uncertainties in the sizes of these extreme stars. For example, one extragalactic star, WOHG 64A, was later found to shrink significantly after it transformed dramatically into a yellow hypergiant. Canis Majoris is surrounded by a vast, dense and unevenly shaped red reflection nebula. The total mass of material expelled into this nebula is estimated to be between 0.2 and 0.4 times the Sun's mass, and its temperature is around 800 Kelvin, according to models of dusty stellar atmospheres. The inner shell of the nebula is about 0.12 arcseconds across, corresponding to roughly 140 astronomical units, or 0.0022 light-years, assuming a distance of 1,200 parsecs. The outer shell stretches to 10 arcseconds, equivalent to about 12,000 astronomical units, or 0.19 light-years. The nebula is so bright that it was first observed on a clear night in 1917 with an 18-centimetre telescope, and some of its brighter clumps were once mistaken for companion stars. Using the Hubble Space Telescope, astronomers have shown that the nebula has a complex structure of filaments and arcs caused by past eruptions, similar to the structures surrounding the post-red supergiant yellow hypergiant IRC plus 10420. This similarity has led researchers to suggest that Canis Majoris could evolve to appear bluer over time. The ratio of gas to dust in the nebula is unusually high, around 500, which is about 5 times greater than typical red supergiants. Over the past 25 years, 6 major outflows or ejections of material have been identified from the star, with the earliest events occurring roughly 100 years ago. Based on this, Canis Majoris appears to have entered its currently active phase, characterized by relatively frequent massive outflows around 1,200 years ago. While the exact cause of this activity is not fully understood, it may be linked to changes inside the star, likely in the structure of its convective layers. The total mass expelled during these episodes from 4 observed clumps exceeds 0.05 times the Sun's mass, implying an effective mass loss rate of at least 1,000th of the Sun's mass per year over 30 years, assuming a total of 100th of the Sun's mass for the largest clumps, W1A and W1b. These discrete events dominate Canis Majoris' recent mass loss history and explain why it has such a high rate of mass loss. Although Canis Majoris is unusual, other cool supergiants like Betelgeuse and the possible post-red supergiant K-type hypergiant RW Cephei have also shown surface outflows recently. Observations of their dimming events indicate that such high-mass surface ejections are relatively common among massive cool stars and contribute significantly to their overall mass loss. Canis Majoris is a highly evolved star, yet it is less than 10 million years old. It likely began life as a hot, dense O9 main-sequence star, about 5 times the radius of the Sun. Its rapid evolution is due to its high mass, and it is now fusing helium into carbon on a large scale. The red hypergiant phase is thought to last between 100,000 and 500,000 years, meaning Canis Majoris most likely left its main sequence stage over 1 million years ago. Early researchers once considered it a very young protostar or massive pre-main sequence star only about 1 million years old, often with a circumstellar disk. Because Canis Majoris is highly unstable and loses mass so dramatically through eruptions, its future evolution remains uncertain. Like other cool supergiants, these mass loss events may determine whether the star ends its life as a supernova or collapses directly into a black hole. It is one of the most important evolved massive stars for understanding how extreme mass loss episodes affect the final stages of the most massive stars that pass through the red supergiant phase. Its ejected material also contains a rich and unusual chemistry, with 25 molecules identified, 21 of which are also found around NML Cygni. The ratio of carbon-12 to carbon-13 in different parts of the ejecta is higher than in typical oxygen-rich red giants and supergiants, possibly indicating extra dredge-up linked to the star's surface activity. Studying these ratios in connection with separate outflows, arcs, clumps, and their expansion ages may provide more insights into the star's current state and eventual fate. Scuti, also known as BD-12 degrees 5055, is a massive red supergiant star that lies about 5,900 light-years away from Earth in the constellation of Scutum. This star is not steady in brightness. It is a pulsating variable star. At its brightest, it shines at magnitude 8.29, and at its dimmest, it falls to magnitude 10.56, which makes it far too faint to see with the naked eye. Scuti is famous for being one of the largest stars ever discovered. Its radius is estimated at 909 times the radius of our Sun, which is roughly 632 million kilometers, or 4.23 astronomical units. To put this into perspective, if Scuti were placed at the center of our solar system, its surface would extend beyond the orbit of Mars, possibly even reaching the asteroid belt. Its enormous volume is around 750 million times that of the Sun. The star was first catalogued in the year 1860 by German astronomers at the Bonn Observatory during their survey of stars for the Bonner Durchmusterung Stellar catalogue. It received the designation BD-12 degrees 5055, marking it as the 5055th star between 12 and 13 degrees south, counting from 0 hours right ascension. When it was later observed during a second survey, astronomers noticed that its brightness had changed slightly, revealing it to be a new variable star. Following the standard naming convention for variable stars, it was named Scuti, making it the 38th variable star identified in the constellation of Scutum. Scuti is positioned a few degrees north of the A-type star Gamma Scuti, and to the northeast of the famous Eagle Nebula. Despite its incredible intrinsic brightness, it only reaches a 9th magnitude appearance when viewed from Earth. This is because it lies far away, and in a region known as the Zone of Avoidance, located within the dense Cygnus Rift. The star is surrounded by clouds of dust, giving it a deep red glow. Classified as a semi-regular variable star, it pulses approximately every 740 days. Earlier measurements, based on an older estimate of its radius of 1,708 solar radii, suggested that these pulsations could either be an overtone of its main pulsation or the fundamental mode if the radius was smaller. In the middle of 2012, astronomers used amber interferometry with the Very Large Telescope in Chile's Atacama Desert to study 3 red supergiants near the center of the Milky Way, Scuti, Scorpii, and KW Sagittarii. All 3 stars were found to be more than 1,000 times larger than the Sun and over 100,000 times more luminous. Using the Rossland radius, a measurement related to where the star becomes transparent to light, and distances adopted from earlier studies, Scuti was determined to be the largest and brightest of the 3. At that time, its radius was calculated as 1,708 plus or minus 192 solar radii, equivalent to approximately 1,188,000,000 kilometers, or 7.94 plus or minus 0.89 astronomical units. Its angular diameter was measured at 5.48 plus or minus 0.10 milliseconds, and the assumed distance was 2.9 plus or minus 0.317 kiloparsecs, which is roughly 9,500 plus or minus 1,030 light-years. Its luminosity was calculated as 340,000 times that of the Sun, with an effective temperature of 3,365 plus or minus 134 Kelvin, suggesting an initial mass of around 25 solar masses, possibly up to 40 for a non-rotating star. More recent measurements in 2023 using multi-messenger monitoring of supernovae suggested a smaller radius of 909 solar radii, a lower luminosity of 124,000 times the Sun, and a slightly higher temperature of 3,550 Kelvin. Parallax measurements from Gaia's data release. 2 indicated a parallax of 0.6433 plus or minus 0.1059 milliarcseconds, implying a closer distance of roughly 1.5 kiloparsecs or 4,900 light-years. This closer distance would suggest smaller values for luminosity and radius, around 86,300 to 87,100 times the Sun, and 755 solar radii respectively. However, these Gaia measurements may be less reliable due to high astrometric noise. A re-evaluation of its distance in 2021, using Gaia's early data release 3 along with colour and apparent brightness, gave a more reliable distance of approximately 1,800 parsecs, or 5,900 light-years. Scuti has no known companion star, so its mass remains uncertain. Theoretical models estimate it to be between 7 and 10 times the mass of the Sun. The star is steadily losing mass at a rate of about 0.000058 solar masses per year, creating a vast and complex surrounding environment of gas and dust. According to current models of stellar evolution, Scuti has already begun fusing helium in its core, while continuing to fuse hydrogen in a shell around the core. Its location deep in the Milky Way disk suggests that it is rich in metals. Eventually, the star will start producing iron in its core, upsetting the delicate balance between gravity and radiation, leading to a core collapse supernova. Before this ultimate explosion, it is expected to evolve back to hotter temperatures, possibly becoming a yellow hypergiant, a luminous blue variable, or a Wolf-Rayet star, which would drive strong stellar winds that strip away its outer layers and expose the core. In the end, Scuti will explode as a type E, IB, R-ion, or type IBIC supernova.